We really want to welcome everybody here. We're at the beginning of a process, and we're thrilled you're here. So we'll learn a lot. We're going to count on your feedback as we go through this, and we'll get there. Some safety things. The exit aisles are up there, and you can go out the doors that we have in the back, and then you go to the far end of the parking lot if something should happen that requires leaving. Ben, did I get that right? Okay, cool. And then the most important thing I'd like to do is I'd like to introduce Ellen Ochoa, who's our Center Director for the Johnson Space Center. She's going to say a few words. She's a big supporter of trying to figure out how we get to Mars, and we're thrilled she's here. And then that's it. Ellen Ochoa.
Well, thank you. It's my pleasure to welcome everybody here on behalf of Johnson Space Center. And first, I'd like to start by thanking our host, the Lunar and Planetary Institute, with whom we've had a long and fruitful partnership here at JSC. This workshop is an important collaboration between the Science Mission Directorate and the HEO, Human Exploration and Operations Mission Directorate, where the communities can get together and start identifying locations, obviously with interesting science return, but also locations with potential for resources that are required to support humans, where we can start to define or refine concepts for crew to conduct operations on Mars, and help define the precursor measurements that we can get that will be needed in order to advance human missions to Mars. At JSC, we're more than a little interested in humans landing, living, and working on Mars. In fact, almost everything that we do at Johnson Space Center is really designed to get us to that point, safely and affordably and sustainably. Obviously, we operate the International Space Station day in and day out, and part of our job is to make sure we do that safely and effectively. But we're also using it as a test bed for future human exploration. And part of what we do on that is understanding more about human health and performance for long-duration missions. So we have experiments that are going on board. We use astronauts as test subjects, of course. We're in the middle, a little past halfway for the one-year mission, where Scott Kelly and Mikhail Kornienko are staying 1 year on board, and will give us sort of that first initial insight into changes that occur in the human body over a period of time that might be different than what we see on 6-month missions. And of course, Scott is also participating in the twin studies, where serendipitously we have a control on Earth for him, his twin brother. And so it's we do think that personalized medicine is going to become more important in the future. And we're learning from some of the experts that people have different responses to radiation, for example, and that may be something will be really important to us in the future. We also use ISS to test systems, not just humans, but other systems, subsystems, components, and operational concepts and protocols, and with that eye toward what do we need to learn for going to Mars. ISS has also provided us with many years of experience in working in a multi-agency and a multinational collaboration, which we believe is also likely to be the model for exploring Mars. We're also developing the Orion spacecraft with our partner Lockheed Martin, and of course that's a critical component to getting crews beyond low Earth orbit, and importantly also getting them back safely at the end of a journey when you're coming in at much higher velocities than we do from low Earth orbit. The Orion program has just completed its critical design review board, and it's also in the midst of building hardware for the test flight that Orion will do on the Space Launch System rocket that's planned for 2018. We also do a variety of technology development at JSC that's really prioritized on future Mars exploration, certainly in areas like life support, advanced suits, automated rendezvous and docking, robotic assistance and robotic mobility. And we have a near-term focus as well, where we're looking at the proving ground missions that will likely be more in the lunar vicinity in the 2020s, where we'll demonstrate a lot of the technologies that will be needed for eventual Mars exploration. And of course, we have our Astromaterials Research and Exploration Science Group that continues to bring unique sample science skills and analysis capabilities to Mars exploration. In fact, recognizing the importance of integrating exploration and science, last year I created an organization at Johnson Space Center to do just that. So we've put our science group in with I'm sorry, I'm hitting that button, aren't I? Sorry.
The button.
But we've integrated our science group in with people who do human exploration architectures and more deep dive concept studies. Our center chief technologists and chief scientists are in that organization. So as we look at where we want to focus resources in terms of development and exploration in the future, we have all the right people talking to each other. While a human landing on Mars is still a while off, the focus here is learning more about potential landing sites in the nearer term so that we can make good use of the existing assets that are around Mars to collect the pertinent information. And so I think it's really exciting that we're starting to do that now and trying to make sure that we use those assets in the best way possible to get the information that we'll need. It's important to consider how crew members will actually operate in the Mars environment from the beginning of our planning, rather than later, when choices sometimes are already made that can affect safety or operability or affordability. And so I'm happy to have our flight operations team at JSC represented at the workshop and including a presentation later today. Of course, our first speaker is extremely well qualified to speak on both scientific and operational aspects of human space exploration. I think John Grunsfield really needs no introduction to this crowd. He's an astrophysicist and an astronaut who flew on 5 space shuttle missions, including 3 to repair and upgrade the Hubble Space Telescope. He has previously served as chief scientist at NASA, as deputy director of the Space Telescope Science Institute, and currently he is the associate administrator of the Science Mission Directorate at NASA. John.
So thank you very much, Ellen. I can stay here.
All right, just
A really pleasure to be here. I think it's really exciting that we're all here to talk about this subject, especially since not too many years ago we weren't even allowed to say Mars or humans to Mars. It was accessible planetary surface. How many people remember that? Yeah, that was pretty frightening time. So, I mean, it's incredible that we're here. And of course, I have to start with a Hubble image as the chief Hubble hugger. And our knowledge of Mars is really, quite a bit further than it's ever been before. As Charlie Bolden says, we're closer to Mars than we've ever been. And if you look in the night sky tomorrow morning, if it's clear here, you'll be able to see Mars. And strangely, it looks a little bigger. I can't tell you why. Something Ellen didn't tell you is that she was hired in the class of 1990. I was the class of 1992. And for both of our classes and many before and a few afterwards, we were told we were the class that would set foot on the moon and later Mars, that one of our classmates would do that. Shortly thereafter, we weren't allowed to say surface of Mars anymore, so it wasn't at all disheartening. But so this time and this group and this effort, let's really do it. There's no question in my mind that we have the technical capability. We all have the interest and the will. We need to work hard to get the rest of the world on board with us. And I don't want to specify which part of the world, since most of the world either thinks we've already been on Mars or is totally behind us. So it's very exciting. So I'll start that with my task right up front is, make sure you're a good communicator. Talk about this. Talk about our journey to Mars. Be adventurous. Speaking of Journey to Mars, this is the obligatory Journey to Mars poster, if you will, and it talks about the things that Ellen talked about. It talks about our Earth-reliant mode, our space assets that we have orbiting the Earth, such as the Hubble Space Telescope, our International Space Station, our efforts to get off the planet. It turns out it's really hard to get off the planet, as we know. Moving out into what's being called the proving ground, a place that we can try out our exploration systems, eventually leading to going to Mars in Earth-independent mode. Of course, why are we here? We're looking at potential exploration zones for human missions to the surface of Mars, but really this is the beginning of the conversation, because we now have, general agreement that, the stretch goal, if you will, I think it's the next goal for NASA is putting humans on the surface of Mars. We want to have the conversation about what are good landing sites, to put planetary scientists and astrobiologists on the surface where they can live, where they can explore, where they can really make transformative science about, are we alone in the universe? What kind of resources do we have on the surface of Mars that we can use for further exploration? Specifically, let's identify candidate locations that we can use the existing resources, Mars Reconnaissance Orbiter, Odyssey, Mars Express, maybe Curiosity and Opportunity, to follow up while we still have them. These things won't last forever, and so there is a real sense of urgency, and I hope you all have a sense of urgency in that. That's why we're here. And define a set of measurements which would enable future orbital and surface precursor missions to refine the candidate sites and identify new sites for human exploration. We shouldn't have the expectation that we will, by chance at this event, find the first landing site. It might happen, but we really should identify locations that are candidates. We're not really here to select that final location, but this other process. If it happens, it'll be really great, and you'll be able to trace back and talk to your students and kids and maybe grandkids. I chose the site where first humans set foot on Mars. But Mars is a really big planet. Think about with Mars Reconnaissance Orbiter. In high resolution, 30 centimeters or so, we've studied less than 3% or about 3% of the planet. There's a lot of Mars still to go, and it's a very complex planet. But even selecting the criteria by which we'll decide if this workshop can come up with a good list will be really helpful. Of course, we stand on the shoulders of giants. That's our favorite Martian, Carl Sagan, next to a Viking mock-up. I'd like to say he was on Mars, and who knows, he may be. I had the privilege of giving the Tim Much lecture at Brown University last Thursday, and so Viking 1 is the Tim Much Memorial Site, and there's a plaque signed by the NASA administrator. At the bottom it says "emplaced," and there's a blank. Okay, so there's one of your landing sites. Somebody's got to go place that plaque. Maybe not the first time, because Viking set us back. For 20 years we said, well, Mars is a dead, boring planet, let's not go back. But we're back. We're on Mars today, and it's incredibly exciting. The things we're learning from a science perspective are absolutely astronomical, but even more so the things we're learning, for instance, about Mars' atmosphere. It has nitrogen, trace nitrogen, percent or two, but that's really important for human explorers. It has reasonable humidity for an extremely dry, low-pressure desert, but it has humidity which is potentially usable. At night, the air gets saturated basically, and we see, at least the Phoenix landing site, we saw frost and snow, water snow. So this is an incredible planet. I am absolutely convinced we can live there. I think there are very few obstacles other than technological and engineering, and the scientific bounty will be phenomenal. So our current plans for Mars include the missions we have now. We're working towards a March launch of the InSight rover. The Europeans will launch Trace Gas Orbiter, ExoMars in 2018. We'll have a Mars Organic Molecular Analyzer. The U.S. is contributing to that rover. And in 2020, we have our Mars 2020 rover. And you can look at it as an opportunity or a liability, but the 2020 slate is blank. And so some of the discussions we're going to have here are going to help inform what we will do in those 2020s, leading to hopefully humans are on Mars in the 2030s and landing shortly thereafter, or at least some point thereafter. The Mars 2020 rover is going to be a great exploration machine. I don't want to go through all of the elements of this, but there's some that are just going to be fantastic, one of which is RIMFAX, which is a ground-penetrating radar. So as it drives, we're going to get an image down hundreds of meters at high resolution of what's down there, which for a geologist is great, for a hydrologist might be great if we see some kind of underground ice sheets, highly reflective ice sheets. We have some pretty amazing analytical instruments on the mask. We have SuperCam, we have the son of ChemM, so multicolor lasers. We have a great follow-on to the REMS weather station. We have META from the Spanish that'll give us more data about the atmosphere. And we have something that's truly unique for a mission to Mars that's of significance, and that's called MOXIE. MOXIE is not a science mission. It's a human spaceflight, space technology mission, which is to bring in atmospheric carbon dioxide, split off the oxygen and tank the oxygen. This is our first in situ resource utilization experiment. It's still an experiment, but we're actually going to demonstrate it on Mars. Sure, we could do it in a chamber here on Earth. People are doing it right now, but we're going to do it on the surface of Mars. This is the first wave of ISRU, I hope. So I want to take a minute and just do an experiment. You can tell me at the break whether it's successful or not. I had a rather uncomfortable seat on the airplane to prepare my remarks this morning. This is just an image of Gale Crater, but I'm going to read you a letter. You can tell me what the date is afterwards if you'd like, but this is from a Mars explorer to his daughter. Dear Sarah, wow, I miss you so much. We've been so busy I just haven't had time to write since we landed on the surface of Mars. I hope your thesis defense preparation is going well. You know I wish I could be there in person, or at least online, but the 20 minutes time delay just doesn't make that possible. The organics you've identified in the plumes on your rope are going to change the world. You know that, don't you? It's only been 4 days on the surface, but already we've made a lot of progress. Our landing was right in the center of our ellipse, so we were able to make our first surface sortie over to the 2026 rover and harvested the enhanced MMRTG with just a short walk. It's still providing 80 watts of power, Still providing 80 watts of power, but more importantly, it's keeping us plenty warm in the hab. Now we can work without our down suits on, and I had to unzip my sleeping bag last night to stay cool. Much better than our trip to the dry valleys in those flimsy tents. So far, no tardigrades, though. See, how many jokes can you tell like that to an audience where they laugh? Also, no whining anymore about minus 40 C. It got down to minus 80 the first night here. The winds were howling, according to the Spanish super REM, but we didn't feel or hear anything. Just not enough rho v squared. See? We also picked up the samples from Mars 2020 rover, and were able to get a core sample from 5 meters below one of the sample sites. Terry's already done one run on the mass spec and confirms the existence of organics in the deeper mudstone. And from the surface cores, we'll be able to calibrate the degradation by cosmic rays as a function of depth. She's working on getting the scanning atomic force microscope up and running to study some really interesting black inclusions from the deep samples. Yesterday, on our second sortie, we commissioned the rover and drove over to what we thought, based on the overhead measurements, was a lava tube and a volcanic dike intruding into the sedimentary basin. In fact, we picked this site because the laser altimetry indicated a good ramp into the interior. However, when we got there, we indeed found the ramp, but it looks like a giant ventifactor, a kind of deep grotto excavated by wind, and lots of time. We erected the inflatable shelter there to provide us an emergency hab in case of a severe solar event. In the long run, future crews can certainly make use of the grotto for protection on long-stay missions. I did try out the new hyperspectral HoloLens projector in the helmet, and it didn't disappoint. There's no question there are lots of hydrated perchlorates at this site. I picked up a couple of kilos of samples that we've got in the sample airlock now, ready to transfer to the glove box. Funny that we came all this way to get samples, and I won't be able to handle them with bare hands. We're going out again in a couple of days to deploy the Watney rover. Silly acronym, Water Acquisition, Traverse Navigation, and Water Acquisition, Traverse Navigation, and Interrogation rover. Don't know why JPL called it that. The plan is first, I've got slides to go with this. The plan is for us to climb up to the recurrent slope linear above us on the crater rim. I sure hope it doesn't get stuck. While I'd love to climb up and recover it, we're restricted on this trip due to planetary protection concerns. That's the Watney rover there. Ignore Svalbard in the background. Don't want to contaminate Mars with us dirty humans before we find out if there's life here now. We've only got another 2 weeks on the surface before we head back to orbit and then home. I can't wait to see you. We should be able to FaceTime again in about 6 months when we get close enough to Earth. I can't wait. I'll try to pick up a good Mars rock souvenir for you. Love you, Dad. So there's picking up the rock souvenir. This is famous Pat Rawlings drawing, which when I look at it, I always go, look, basalt. Anyway, really, I think it's so exciting that we're here. This is the conversation we need to have. Again, some of the outcomes we hope we get from this workshop, that I hope all of you hope, is to leverage our current assets at Mars to start picking possible landing sites, inform our efforts to find what we need as far as future reconnaissance at Mars in the 2020s, to drive where we send robotic landers to get ground truth with what we are seeing from orbit, future rovers, to kind of certify our landing site for scientific exploration, and begin work on the instruments the planetary scientists and astrobiologists will need on the surface as they explore. And with that, enjoy the workshop. I'm very excited about it. I hope you are too. We have a long road ahead of us, but we get to have this conversation, and we're taking another exciting step towards human on Mars. Thank you very much.
Actually, change of plan, because rather than listen to me, we don't have any questions. Go on, don't be shy. Because I could go on for a long time. Well, maybe if you think of them, we have a questions and answers session at the end. I'm sure people will be braver by then. Okay, so my name is Ben Busty. I'm the other co-lead of this activity with Rick. And there's two parts to our tag team talk here. I'm going to give an overview of the goals of the study and how it came about a little bit, and then Rick is going to concentrate on the goals of the workshop. So it says here, sending humans to Mars is a top NASA priority, and the agency believes that such missions will significantly expand the amount of science which can be accomplished on the planet. And so the original sort of goal behind this activity from a HEOMD perspective was, as Rick alluded to and John alluded to, we have these assets on the surface. They won't last forever. Are there data that HEOMD would like acquired that helps with the planning of eventually humans on Mars? And once we started this activity, it really sort of expanded quite significantly to in a good way, into what we have here today. And we have a very experienced steering committee, both from the science side and the human exploration, the engineering side, the in situ resource utilization side. I think they're all here today. Some nomenclature as we go forward for the next sort of 2.5 days. You'll hear science site or science ROI or region of interest, which represents an area of high scientific interest for human exploration. Again, we've been focusing, and you'll hear more about this, on the science that is achieved by having humans there. That humans are enabling from a science perspective. There's the landing site, which is an area amenable for a safe landing given entry, descent, and landing constraints. And then habitation site, which is a region for where, not an insignificant area, which we would need to set up the infrastructure that we need to support crews. And one big difference in when we did this compared to perhaps what had been, many of you will be familiar with DRA5 and activities like that. The big difference is we were looking at an area that multiple crews would visit. So the concept behind the exploration zone is that this is it's a zone because we expect the crews to have mobility, and not insignificant mobility. Right now we're talking about 100-kilometer capability in a pressurized rover. So that's a large area to explore, and we intend, the plan is to send multiple crews to this exploration zone. So you need to have a lot of good things, good science for the crews to do, but also the aspect of what do you need, what do we need to learn about local resources, because the idea would be, obviously, the more you can live off the land, the more achievable that this is. So this is the exploration sort of layout consideration. It's approximately 100-kilometer radius circle on Mars, with multiple science regions of interest of different scales and different science types. Potentially multiple resource regions of interest, ideally located fairly close to the center of the exploration zone, where one would expect the habitation area to be. And you'll hear lots more of these ROIs in detail in the upcoming talks. So we showed this, just you won't be tested on it. This this is what happens when you have your first couple of days, almost a year ago now, and try and work out what you're trying to achieve. And the reason for showing it is the 3 boxes on the left, the science objectives, the engineering and operational constraints, and the ISRU civil engineering. They were the real. We realised that was the key input into trying to have as an output what are the good exploration zones, and you're going to hear a talk in each of those 3 topics. So we're almost all the way here now on the right at the workshop, and the deliverables will probably have changed somewhat since when we first started. As John Grunsford alluded to, we're not sort of prioritising here. Part of the process is going to be what is, does the concept of an exploration zone work and what makes a good one, and Rick will talk more about that. So we developed with the science community using, by way of a MEPAG science analysis group, and they looked at how humans on the surface can best be used to significantly enhance the science that will be achieved, and the next talk would be on that. The engineering constraints was particularly interesting to me personally. The Evolvable Mars campaign folks, they brought a very different view to the table of how we'll explore Mars. This idea that you'll go with multiple crews and you will have significant mobility really does change what you can expect to be able to do. And also the idea of a precision landing, that also is a fundamental change. You've got a large region to explore, but you only need a very small portion of it to be flat, to first order. And at some level, you can we may well find out you can almost ignore. I get rotten fruit thrown at me for this, but you could almost ignore the issue of a safe landing, because if you only need a 100-meter good area, the chances of finding that in roughly the middle of a 100-kilometer circle is probably pretty high, or at least we hope so. It's one of the things that we would want to look at when we, down the road, do some detailed studies on what we're calling prototype exploration zones. And finally, we had the in-situ resource utilization civil engineering working group, and they were tasked with developing a set of objectives that satisfy NASA's goals of the key word here is sustainable, and the more you can use what's there, the more sustainable it is. And again, you'll have a detailed talk on this following this one. And finally, another key thing that we knew from the beginning we wanted this activity to consider is future reconnaissance data needs. I mean, we have wonderful data of Mars now, and the real question is when we start to, in this room, when we start to talk about what analyses do we want to do of these potential exploration zones to answer the questions we want answered, what data, as was the original purpose, what data do we want acquired by current assets, but also are there really key data sets that would be enabling in us doing this process? So with that, I will happily hand it over to Rick, who's going to concentrate on what the goals are of the next 3 days.
Okay, thanks, Ben. So before, I'd like to add one thing. The work that we've done today has really been completely joint between the human spaceflight side and the science side, which has really been very exciting. So the results you're seeing today are really that combined effort. Since then, STMD, which is the other big mission directorate playing in the Mars field, they have joined this effort as well. But really what this workshop is about is broadening that process so that we can start really honing essentially a set of concepts down. And so we're not going to be shy about it. We're proactively soliciting your inputs, and we count on you not to be shy, because it's a process that we want to hone down. And so what we're going to, these are essentially, if you will, the goals of the workshop. And again, you'll see on Friday where we try to really pull it together. So we're going to count on you to actually be a part of that. And so first one is, Ben kind of alluded to it, which is the existence proof, if you will, that an exploration zone makes sense. We think it does, but we don't want to bias that. We need people to look at it. But the fundamental concept is very much like McMurdo Station in Antarctica or ISS, where you actually have a base, and you'll hear more about it, and you can build up supplies, logistics, and all that kind of stuff to actually keep people alive and give you options when things go wrong. Next thing, we know very well how to image for landing sites and also science regions of interest for the rover programs. We are less clear on that, on what actually needs to be done for an exploration zone. Your inputs are going to be key to helping hone that down this week. But you're talking a 100-kilometer radius circle. It's a big honking thing to use. I mean, I grew up on a farm, so that's the terms we use. But we don't know how to do that yet. So part of this is we're going to draft those things. We're going to get your ideas. We're going to build essentially what would become an announcement of opportunity that would be open to everybody who's participating and others. We will probably, our intention is actually largely using this workshop in format. We'll probably pick some prototypes to try to make sure that the draft AO makes sense. In other words, there'll be a guinea pig. And then we'll get out, hopefully, a more robust acquisition announcement of opportunity that would really be the meat of what we're trying to do heading towards another workshop. John, as well as Ben, alluded to this. Then the discussions that we've had, it's becoming increasingly clear that there are, particularly in the area of water, as a resource, that we are maybe deficient on reconnaissance at Mars. And so we believe that we can use all your thoughts and ideas to help us hone down that process of what is it that we need in future reconnaissance at Mars. And so that you'll see that going through here. Reference exploration zones for engineering analysis. So in general, you start running into, can you do the traverses, that kind of thing. And it's helpful to have exploration zones, much like we've already done it with the rover program, where they're stressors, if you will, in terms of the engineering. Not so much for entry, descent, and landing for the reasons that Ben alluded to, but there are other reasons why we would definitely do that. So we already talked about the inputs for the AO. And the last thing is, this is a multi-year process, just as it is for the rovers. We are going to be soliciting your input for lessons learned and next steps. And you'll see, in fact, I'll flash through it, and also the date of the workshop. But there's already a set of questions. They were sent out to you in an email yesterday. And so this is our draft set of questions. We're counting on you to come up with some other ones. And so you'll see that these are the ideas. And so we're going to visit these throughout the week, and we're going to count on you to actually help us make a good, even better set of questions and start forming those answers, if you will. And I think that's pretty much what I wanted to say. And then it is integrated. So we're really looking at I call it the Venn diagram, but the intersection between not only science, but human spaceflight and technology development to make sure we really have a good set of answers. So no one in this room, I'm the first at the list, has a total picture of this whole thing. It's only about working together that we're going to be able to figure it out. And that's kind of a key piece. We wanted to mention a few things about the agenda too, since we're doing this. Today you will be getting a series of overview talks. The intention of those talks, a lot of that information is actually on the website already. You probably saw it. For those of you developing proposals, you saw those. But we want to kind of let you hear from us what those things are, so you can ask us questions and help inform that process. And so it covers the gamut. It covers the three areas that Ben talked about. And it also covers planetary protection, all the crew and operations, all those components that are key to pull an integrated answer together. And I do want to mention this. Y'all will notice, I think there's 45 landing site proposals out there. It's a really cool proposal. You'll see them out there. We do want, feel free, there'll be Sharpies out there because we want everybody here to sign this thing. And then what we're going to do is make a high-res picture and make it available to everybody so that everyone can have one of these things. So you will see there's two of them, so sign two, in case someone goons one up with a Sharpie. And I came out of the space shuttle world, so we worry about those things. Okay. Then on Wednesday, we have multiple sessions where we've got, you'll sort of see the mid-latitudes and the high latitudes is sort of the breakdown in terms of these different proposals for landing sites. There is an optional dinner and a movie, The Martian. That would be very appropriate for us. So if you would like to join us, we would love to have you. We do have a head count. Andreas is right here. Please let him know if you would like to be on that. Thursday, multiple sessions. Again, we will have a post-workshop talk by Jim Watson, who's also the Mars Program Director, and Jim Green, the Director of Planetary Science Division. And then there'll be a wonderful evening reception that everyone is invited. That ExploreMars.org is hosting, along with BAHAP, which is a local community one, and others. And Chris, wherever you... Yep, Chris there. Chris, who else did I miss on that? Other sponsors that y'all have... Okay, cool. So I'm sure you all are all invited to that. And then the big thing is we are going to have a discussion about the sites that we should look at maybe that look most promising. You'll get more information about this for doing this prototyping, so we can inform the development of the announcement of opportunity. And we'll talk more about that on Friday and during the week. The other thing is these questions, which we really need everyone to look at. We're going to be drilling in on those things throughout the week, and we will be pre-drafting that as we go through here so that we actually will have a workshop statement. Those questions, we are going to try to get as many of your inputs by the end of the week, but then we're set 2 weeks out so that you actually have some time to think about it and give it to us. So it's not like we have to all be done on Friday. I think I might be done. Yes, I am. Ben, should we ask questions real fast? So does anyone have any questions that Ben or I can try to address? Yeah.
The non-ISRU and non-civil engineering, the reports on that and the presentations, are those available anywhere? I wasn't able to locate them, and I think that would inform a lot on what the significant mobility systems and everything are.
Oh, yeah. So we will show you where they are. Yeah, and we definitely will make them we can actually PDF them and send them out to everybody. I would say one of the things which we really, I think we saw an email from Jim Head earlier today. This is about building an integrated community. And so your question is very key. So how do we get everybody to have all the information and figuring out what we need to do next? Any other questions that we can try to answer? Yeah. Oh, yeah. Anyone else? Okay, great. So Ben, what's next? Okay, pause. So Lindsay Hayes will actually give you some background information on the little forms that we want you to be actively thinking about these exploration zones that are being proposed. And this is a questionnaire. We've done our best to do it, but we're going to count on your feedback to even make it better as we go forward. So thank you.
Thanks. Let's see if I can. Do you want to navigate me to the?
Are you going to leave the podium?
Is it over there? Yeah, that'd be. No, not the microphone. Can I use the? Oh, here it is.
Yeah.
There we go. Okay. So first of all, thank you all for being here and making your way down to Houston. My name is Lindsay Hayes. I work at the Mars Program Office in JPL. I have been a part of this Human Landing Site Steering Committee since the beginning. And so as Rick gave a great introduction, we are very interested in your feedback in these exploration zones. Those of you who are used to landing site processes for robotic missions are used to this idea of getting the feedback from the community. You guys, having proposed and been a part of this and selected and choosing to be here, have a unique vision and a unique understanding of what these exploration zones are. And so we want to make sure to get your feedback on how they are as a group and the whole assemblage of them together. So the polling strategy that we're going to employ here this week has sort of 3 parts to it. These are available to all participants, all of you whose faces I can see in this room now, and anybody who's listening online on the Ustream account. The 3 parts to this are the full rubric that you guys have probably seen, especially if you are one of the presenters. It was a couple of the slides and the template, a notes sheet, and a polling sheet. So the full rubric is going to be available online. We have a Google Drive version of it. So as each of the presentations get loaded, we're going to have Josh over here is going to be pulling that information out of the rubrics that are on the individual presentations and filling out the version on the website. I don't think it's quite loaded onto the website yet, but this is something that we should have up by tomorrow morning. So those of you today, sorry, we'll get it up by tomorrow. This is going to be publicly available online. And at the end of the sort of 4 or 5 easy presentations that we have, the sort of grouped, we're going to have these integrating discussions. And at that point, we're hoping to be able to load this full rubric up onto the screen so we can discuss it and look at and sort of understand how different sites have filled it out. And we can discuss this as a group. So that's the first part. You guys are not responsible for individually filling this out. This is information we're getting from the presentations. The second part is the notes sheet. Now, this is something that was out front when you guys came in, unless you came in very early, at which point it was not. Luckily, before we see any of these presentations today, we'll have time to run back out and grab them. It looks like this today. It will have more lines or more rows in it for tomorrow and the next day. Sorry. This one here is a reduced version of that full rubric. You can see it has a bunch of columns here, but it's not all of the columns that are in the full rubric. The idea here is that these are the threshold criteria only, and this is a way for you yourselves to look at the presentations, get a sense, see how well the presenters make their arguments for various criteria, and then also keep your own notes here. This will not be collected. This is for you guys. If you choose to fill it out, great. If you choose not to fill it out, you will not be graded on work that was not done. We have not given, we haven't said this is how to fill this out properly. This is totally up to you guys. If you want to use X's and O's, if you want to use stars and comets, whatever you want to use, feel free to do that here. This is, and you can assess for yourself. Oh dear. Here we go. You can assess for yourself how well the proposed ROIs in this EZ will meet these criteria. So this is just for your use. The third piece is the polling sheet. Now this is something we will be collecting. Today's version, the printout actually is a little dark. Sorry about that. But this is what we will actually be collecting. You'll see that there's the main sheet on the front and questions 1 and 2 are outlined. There's question 3 on the back, and this is sort of what Rick was alluding to earlier. We're asking specifically that you only respond to the presentations that you attended. So if you step out and have a conversation with somebody else, totally fine. Please only respond here for the ones you attended. I will let you guys judge whether or not you have attended mentally or not attended mentally, and we are not, taking attendance or anything. But this is sort of on your honor. And then feedback, we'll collect these. We're going to have one for today. We'll have one for tomorrow, and we'll have one for Thursday. We're going to collect these at the end of the day. Some of those notes are up here. You can see, please enter only for the ones you've attended. Again, use your judgment. And there's additionally 2 questions below. But I'll get to those in just a second. You can see the columns here. The first question, do you think the proposed EZ merits sending multiple crews to explore? Remember, and you'll hear a little bit more about this, but the idea is we're not just sending one group of astronauts for a day or 2. We're talking about multiple explorations. So you have to have, a lot of science justification, a lot of resource justification. So that's sort of what we're getting at with this question. Do you think this proposed, and so the responses that you can choose here, we're asking you to choose one. So yes, there's a strong argument for this exploration zone. Possibly, the information is less convincing, or uncertain. The current data is insufficient. This is a little bit on your interpretation, what you've heard from the presentation, how you processed it, how you feel about the way that this EZ, the data, the information that is there. The second question is, do you agree that the requested highest priority EZ data needs, now this is a specific slide that we had in the presentation template, where we're asking the presenters to propose, this is the piece of data or the 2 pieces of data that we think are most important for helping us to better understand this EZ. So that's why that's in quotation marks. It's a specific request, the highest priority EZ data needs from the current assets for both science and resources are the best to sort of improve your ability. What we're asking here is, do you think that the data that this presentation says, this is what we really need, do you agree? Do you think that they have made a correct assessment? If you do, that's easy, you just mark yes. If you don't, if you think that maybe there's something else, they sort of glossed over this other ROI and you really think that it's more important that we get more of that information, that's what this no question is here. So you'll see, I'm going to go back here. You'll see that there's yes, and there's a column for you to mark yes. And then under no, this gives you the opportunity to provide a little bit more feedback. Do you think that we need science data from a different instrument? Do you think we need science data from a different location? Or do you think we need resource data from a different instrument or a different location? This is your opportunity to say, they said ROI 1, we really want to get a CRISM image of this spot here. This is your opportunity to say, yeah, ROI1, I totally agree, but I think you need a high-rise image, or I think you need something else. So this is your opportunity to sort of give us some feedback. We will then work with we were envisioning working with the presenters to get at exactly what if we get, a plurality of responses no here, we're going to work with the presenters to see what might be better options here. So you'll notice at the bottom, with no space to fill in the answers, is question 3 and question 4. Question 3 is a 3-part additional optional questions. You'll notice that this slide here is on the back. And so this gives you the opportunity we've sort of grouped these by the sort of groups that we're presenting or we're going to be discussing in each of the integrating discussions. So you'll get one of these for today because we're talking about one group. You'll get 5 of these for tomorrow and 5 of these additionally for Thursday. But these are these additional questions for you to provide some additional feedback. What are some of the strongest aspects of the EZ as presented? What are some of the weakest? And what do you need to help improve your ability to assess this EZ? This is an opportunity for you to give a little bit more feedback. Write what you feel would be helpful for the presenters, for us on the steering committee, and fill in this here, and we'll collect these along with the polling sheet at the end of the day. Okay. And then the final question, you've heard this idea of prototype EZs. We're going to get a full presentation about this on Friday. There is not space to answer question 4 in any of the polling sheets, but while you're going through and listening to all these presentations, what we want you to be doing is thinking in the back of your head, your top 3 EZs for which a strong case can be made on the current data, which if you remember is sort of the yes answer to question 1, or your top 3 EZs for which the current data is uncertain. So that's the uncertain column for question 1. If you can email those to me by November 13th, we're not necessarily asking you to do this real time. We want you to sort of think about it a little bit, process it a little bit, and then get back to us with this. And these will ultimately help us in identifying these prototype EZs, and that's something that we'll talk about a lot more on Friday. So, questions? Oh.
Question 3 was also they've got 2 weeks.
Yes.
You said handed in.
Well, the paper can be handed in.
But they've got 2 more weeks to think about.
And if you want to add any additional information, you can feel free to email that within 2 weeks. Yeah. For people online. Okay.
Is this thing on? Lee Billings, Scientific American. Can you define a prototype EZ, please?
So this is something we will be talking about. This is what I was saying. We'll be talking about that more on Friday. In general, prototype EZs are, actually, do you want to speak to that?
So again, it's to inform an announcement of opportunity to make sure we know how to do it. We've never picked a human landing site. So we have ideas, but the fact of the matter is we're really cutting new ground. So what we want to do is basically picking a couple of guinea pigs, to essentially help us figure out how we really do this. And this community will need to weigh into it, and then we would then go out with some sort of announcement to the entire community and even solicit others with an opportunity. This is the idea. Hopefully that answer your question.
I think so. So the prototype EZs are linked to the AO?
Yeah, well, but they're not. The AO is actually where the real work's getting. This is to inform what that AO needs to be.
Yeah, I think if you're saying, is the AO going to be just to analyze the prototype EZ, the answer is no.
Right.
The idea of the prototype EZ is to help us work out what kind of analyses do we want, which is why we're picking 2, one from an EZ which is already fairly well imaged, and one which is less imaged because we might need different things done. But it isn't going to be that the AO is just about the prototype EZs.
Yeah. All right.
And the prototype EZs are also not intended to be the best or the most uncertain. They're just sort of, yeah.
And so a follow-on question actually is
Sure.
related to the issue of data needs. So I understand the possibility of saying, okay, perhaps we need additional high-rise data. We'd like to commission sort of bandwidth or whatever for that. But are you also looking for information such as, at this site or sites like it, we think we could make a huge leap in our understanding with a fundamentally different kind of data which we would collect with a future mission. If we had a carbonate mapper or high-resolution radar or something, that would solve X, Y, and Z problem.
So this is also a discussion that we'll be getting into on Friday, and that's sort of the future missions, future instrumentation, and thinking about, what future instrumentation would help us really understand that. For this question, again, I just want to focus, it is the current assets, but we will be getting into a discussion about what is the other kind of data that we need that we can't collect with current assets. But this question is just focusing on current assets, but we'll have a discussion about future assets on Friday.
So, Lindsay, it's Pan.
There we go. You're
So-
directly beneath the light. So you're
Exactly. To
glowing.
get to question 4, there are a few chicken and egg aspects of question 2 and question 3. And one thing that it would at least help me, based upon what I've learned from MSL, is that understanding what level of spatial heterogeneity is revealed by orbital assets doesn't always tell you the level of spatial heterogeneity that's revealed on the ground. So we made some assumptions early on that there would be precursor missions. And so unless we just cede victory right now to Fred Califf and say we're going to Gale, that's a commercial for you, Fred.
And the other 2 people who proposed Gale.
Yeah, there's a lot of stuff that we would want to know. We had X number of precursor missions at X amount of spatial scale to provide us the answers to the questions for number 4. So that the first question is, can we go with an assumption of a specific number of precursor missions? And the second question that relates to how to define a good candidate exploration zone has to do with, is there in mind a minimal separation between resource region of interest and exploration for science region of interest, so that we can lay those puzzle pieces out with the optimal separation as we peruse the zones?
So let me try to address the precursor missions. This is a bit iterative because the agency does not have those funded right now. I think there's a growing recognition that we obviously need to do that to enable human missions, but we don't have those right now. So part of what this process here will do is actually help inform what is needed in those precursor missions. It's not just the landing site or the science that's being done. There's all these other things, but this is a very important step and community, if you will, to help flush those issues out. So I really, and Ben, chime in if you think, it's an iterative process. We're at the beginning of that thing, but eventually your question is spot on. You really would need to know that so you can start doing it, but we're not there yet. So I think we will get there. And in terms of the separations between resource ROIs and IS and science RUs, that's part of what we need to talk about. So you're in the beginning, so we'll have to figure all that out because we don't really have that answer yet. Ben, do you have anything you want to add to that? Okay. Yeah.
University. I had a quick question about strategy, long-term strategy. So the map you showed is like to die for in terms of future exploration of Mars. Anybody who looks at that says, geez, Mars, like there's plenty of places to go. And not only that, they're all exciting, which we'll hear about in the next few days. My concern is that it sounds like a lot of this is related to focusing, down selecting, et cetera. And that concerns me greatly because if we get down to just a couple of sites, I think we've lost a lot of the public's excitement, et cetera. And I really think that's treasure. Plus, it's really important for science and engineering synergism to get us together to talk about these things, not to focus on one thing.
We totally agree with you. This is part of that process. That's why I think Ben even alluded to the fact that we really are not in a down select mode right now. We don't even really know what we're looking for totally. We've spent a year. Let me finish. Sort of honing it down, but every one of you is part of the process of trying to hone that down so that we can build a robust announcement of opportunity to really kind of start into that. But we're just beginning.
It just sounds like it's really competitive.
No, it's not. No, that's not the intent. The intent, frankly, if we just get the science, ISRU guys, and technology development guys all on one team, that's victory right there. that is that massive victory. So go out and say hi to your neighbor. And because that is, and I saw your email this morning, which was great. So that is victory for this week. But we can do more than that. I think we can really do these questions that we have will be key to helping inform things. Ben, what else?
Yeah, Jim, I think as much interest as submitting your top 3 EZs is the rationale for why you picked them, because then from this big diagram we can start to sort through what are the right considerations for any of the sites. It's not so much the final 4 countdown type of approach. It's more why did you pick the sites? What were the rationales? Trying to figure out what defines a good exploration zone. I think that's what we're all after.
Any other questions? Okay, I think we're ready. Thank you, Lindsay.
Oh, good question. We'll have them collected at the front here at the LPI. The question was, where should we hand in the presentations or the pieces of the polling question? And the answer is if you can put them in the front, or if you are online, an Excel version of the spreadsheet will be available online, and that can also just be emailed to me.
All right. Well, I'm happy to be here. I'm here to talk to you all about the HSO SAG, which was that's not me, is it? The remote mic. All right. So the HSO SAG, which is the group that was stood up to look for or basically output criteria, scientific criteria for picking a landing site, or an exploration zone in this case. I'm here representing a large group of people. Many of them are here as well. Many of them put just as much time and effort into this as I did, so they deserve as much credit as I do. So, including Lindsay and Dave Beatty, who are the co-leaders with myself. So, just want to acknowledge them before we get started. All right, and this is the group that was here. We tried to focus the group on, sort of a wide variety of different fields, so try and get as much input as we could into understanding what the science criteria would be for a human landing site on the surface. All right, so these were our requested tasks. So our job is to discuss landing sites and exploration zones, and so we went about it following this pathway, which was a little different, I think, than past exploration zone or landing site workshops. So our first task was to try and understand and look into the future and try and understand what the state of knowledge would be in the 2030s to sort of help inform what would be the important things. Maybe there will be new discoveries, maybe there will be new things that happen that change our priorities that we would have today. The second task was to look at robotic and human exploration together and maybe think about how those things interact and how those might impact our priorities. The third task was to look at formulating a set of science objectives for the human landing mission. And this is a sort of not a set of objectives for the mission itself, but for a set of objectives by which you might choose from to formulate the mission. So we tried to be inclusive and cover all of the different objectives that we think were important for going to Mars, and then with the idea that maybe when you pick a landing site, you might not do some of those things because you just can't. But with the idea that if we have the full set in front of us, then we can use that set to derive, which is task 5, criteria that we would use to pick a landing site. And I want to say that this is by far not the final statement on this. And one of the things I think I'm looking for, and I think Dave too, is feedback on this, on our results, and hopefully we can make it better in the future. All right, so this is how this task worked out. I skipped task 4, as you might understand. Task 4 we're not going to really talk about today, and we didn't really touch on, we didn't get to as much, and that dealt more with implementation aspects, which get complicated. Okay, so we worked on task 1 and task 2, and then those fed into task 3 and task 5, and now we're here in the site selection process, beginning of the site selection process. All right, so the assumptions that we took into account in order to sort of get started on this was a launch date of 2035. We also assumed precursor robotic missions that would have occurred beforehand. This includes Mars sample return, and maybe not necessarily Mars sample return from the landing site itself. And then that the human mission would be composed of a long stay, 300 to 500 sols with multiple people, and visiting the same location on the planet. The other thing would be that the crew capabilities would be able to traverse 100 kilometers away from the landing site, that they would have a fair amount of laboratory facilities of as yet undefined functionality located in the habitat, and we also have substantial EVA abilities to gather samples and do what we need to do. And the other thing is that we focused on science objectives in particular, and science objectives about Mars, not necessarily other things. So our main focus was science objectives about Mars that can be done on Mars. All right, so the big thing that sort of starts this and makes this maybe a little different than what we've done, other landing site studies we've done before for robotic missions, is that we're dealing with this exploration zone concept with a landing site in the middle and a 100-kilometer traverse. And now with this sort of size of exploration zone, now it really sort of opens up to maybe a lot of different things that we never really thought about before. Because before, we have these robots we have to land on top of or right next to the science thing that we're interested in. And the thing we're interested in is really only one thing. But now we can visit multiple places with a really diverse set of characteristics that allow us to really sample a wide variety of different science objectives. And this is the thing that we sort of were hoping for, was sort of making sure that this exploration zone captures as wide a set of scientific questions that we can get, and also the most important ones. Planetary protection. So planetary protection pervades through everything with exploration of Mars. In our case, the way that we had treated it was the idea, it's basically that planetary protection allows for exploration of Mars with a correct implementation. And so we assume that we are going to use the correct implementation and that we will be able to do everything that we want to do. So in that case, that was our treatment. So we didn't place any restrictions on any science objectives based on planetary protection concerns. Okay, so getting into task 1. So one of the things to think about with task 1, what sort of made us think about is that the design for this first mission to Mars, human mission to Mars, will start well before it launches. And the science state of knowledge that we're going to use to define the objectives for that mission will actually have to be set well before too. So we're actually, with a launch date of 2035, we aren't that far away from the science objective set that we would use for that mission. When you think about the missions to come and the amount of data, there isn't necessarily a whole lot that would go. Obviously, new discoveries could provide refinement of science goals and operations. So new discoveries might allow us to say, oh, let's bring this type of instrument for the crew to use on the surface, or other things like that. But the major equipment would probably be set in stone well before that time. So we also considered sort of the missions that might inform our knowledge base, and what are the kinds of things that might impact our state of knowledge. And as you can see, we've got quite a few instruments or missions at Mars today. And we're obviously planning the 2020 rover. We're assuming a Mars sample return lander that occurs before our 2028 date. And there are also plans for other orbiters and potentially other landers as well. So this is what we considered in our consideration. So I wanted to emphasize that these upcoming missions have a really high potential to deliver really interesting, exciting science results. There also is probably a high potential to get science results from the data that we've already collected, as well as ongoing Martian meteorite research and interdisciplinary insights, technological advancements. And there's certainly, definitely low probability, high impact events that could completely upset the apple cart, which would be really difficult to predict at this time, seeing as they're low probability and high impact. There's definitely things that we can't, we call these black swan events that we can't predict at this point. There are definitely things that we could potentially predict that might affect things. This is not an exhaustive list, but we certainly considered potential of these kinds of discoveries that could happen. And basically the formulation was that even with all of this, we felt like the overall goals and objectives, the sort of highest level goals and objectives, would not change dramatically as far as the overall structure goes. What those things are might change, but the overall major goals and objectives would not change prior to the human mission. All right. So task 2, I'm just going to summarize this. You see we'll skip to finding 7 here. One of the things that we thought about, I think is really interesting for this discussion, is that the human and robot interaction, we can really start thinking creatively about this. And you might think about things that, not just how you have a robot next to you while you're walking around on the surface. You might have robots flying over you, scouting different spots. You might have robots that land outside of the exploration zone and analyze things that would help understand the things that you're looking at in the exploration zone. So I think the idea is that robotic exploration might help you really expand some of the exploration that you might do. But it also, we'll want to make sure that the robotic exploration complements the objectives of the human mission as well. All right. Not to discount that there will be probably ongoing science mission directorate missions that might also be occurring at the same time. All right. So now we finally get to the science objectives. The criteria that we used to determine science objectives and to prioritize them, where we prioritize them, was the main was intrinsic scientific merit. We also considered the magnitude of the benefit of a proximal human. So what are the kinds of science that might be enabled by human exploration? What are the kinds of science that it really doesn't matter if there's a human there or not? We also thought about the opportunity that humans provide to make sort of a much more substantial contribution. So you can really think about things that where humans will land and move things well forward. So that might increase their priority. So the prioritization that we did do was fairly limited, and it's really further evaluation of these objectives need to account for implementation factors and other factors as we sort of hone in on what we're doing and how we're doing it. So we really wanted to focus on laying out the objectives. We have a little bit of prioritization that we did do in order to focus the discussion, but not excessively. All right. So astrobiology is one of the things that we did not provide objective priorities. These are the 6 objectives that were identified as being key for astrobiological exploration of Mars. Obviously, you can sort of pair up A1 and A2 as past life, A3 and A4 is extant life, and then also looking at subsurface surface interactions as well as the chemistry, organic chemistry that might be occurring at the surface, and the near surface. Atmospheric science, also, this was an interesting set of discussions because when you're going into it, you sort of think, atmospheric science, they don't really matter. for human exploration. That kind of, we'll put some instruments down and that'll be that. But when you started talking about it, really, brought home some of the things that having a human mission will enable in atmospheric science. So one thing we talked about was being able to much more substantially quantify the atmospheric state and forcings with a much more robust set of measurements. We also talked about some of the information that we'd be able to get about past atmosphere and atmosphere through studying past rocks. All right. And these were prioritized by the team. And these are the geoscience objectives. As you can see, the geoscience objectives were we were lumpers rather than splitters in this case. There are quite a few, and you'll see in the next slide some of the questions that you can split these things into. And the idea is basically, if we did list them all out, it would be rather extensive. So we tried to capture this in a bigger overall arching science objective, and then we also identified some of the other sort of more detailed stuff, questions, and then we use that information to feed into the criteria, which you'll see in the next slide. All right, we also identified cross-cutting objectives, emission access, concentration of water. Some of these things cross-cut between ISRU and also studying the impact of humans on the environment. So when we land humans on the environment, that's going to create a whole new field of studying how humans impact Mars. Okay, so here's our science objective set. And so now what we did was we took the science objective set and we plugged it into, let's see. Yeah, so we plugged it into the landing site criteria. So we took this science objective set and then derived the landing site criteria from that science objective set. And each one of these criteria were sort of drawn from either one or more of the science objectives that we identified. So we sort of feel like the landing site criteria really provide a foundation in the science that we wanted to do. And and you can see that I think it's really important to read the whole text of these landing site criteria. In some cases, the abbreviations on the rubrics are maybe a little misleading or don't capture the whole meaning. So, and that's just necessary because they had to be shortened. So please go ahead and read these in their full text. You can also read this report online. I'd please go ahead and do it. It's got a lot of information which I don't have time to get into. So I encourage everyone to do that as well. All right. One important part about the criteria here is that we have, so we identified threshold and qualifying criteria. And basically, the idea here is that the threshold criteria are the things that we would not want to pass up. So we would felt like that the threshold criteria are all of the sort of minimum set of things that we want every exploration zone to have. And in the case of astrobiology, we wanted to say that it could be and or. So past habitability or present habitability, or both. Both would be better. But if we just had one, then we would be happy with that. And then we have a couple threshold criteria from atmosphere and geology as well, which we felt really are fundamental to understanding Mars and would need to be present in any exploration zone. So a successful exploration zone proposal should provide a reasonable justification. So there's a lot of these which, when you look at them, you're like, well, I don't know how I can tell you if there are trapped gases present, But the idea here is that what we want people to do is to say, listen, this is based on the information that we have, and based on the information that we are sort of inferring, that we can say this. We have a really strong case for thinking that there would be trapped gases here, or there would be rocks that could tell us something about the past atmosphere. We understand, everyone understands, that our knowledge of Mars is still in its infancy stages. This is a whole planet, and its complexity is yet, we're very, very low on the scale of learning about Mars's complexity. So So I think what we're really looking for with these science criteria is for people to make the case for why they think their landing site would meet these criteria. And we also wanted to identify particular data needs for that in the near future with available resources. And let's see, I think I'm almost done here. Yeah, so for a potential 2035 surface mission, we expect that the objectives that we've got today shall be fairly similar, at least in overall topic subjects, from at the goal level from what we have today. We've identified a set of scientific objectives and traced those into landing site criteria. And we felt like the robotic-human partnership would really be an interesting place to sort of better expand our ability to do science on the surface. So thank you all, and I'll pass it off to the next person. Oh, yeah, questions.
Just a clarification question about the role of the precursor missions.
Mm-hmm.
Would you characterize these more as reducing risk for a human mission with science thrown in, or a science mission that would better inform site selection with some human exploration risk reduction thrown in? I wasn't quite sure.
So the precursor missions were part of our assumption, the assumptions that we were given. We didn't do any analysis of what precursor missions should or should not happen, or what there should be done on these precursor missions. This would get into task 4, which was the implementation side of things, which we did not really have a chance to fully address in the time set, the compressed time scale that we had. So I'm going to have to punt on that question. It's not something we talked about. Do we have Mike? Anybody else want to wait?
That's the same question.
Hi. On your slide, you said 100-kilometer diameter exploration zone.
Oh, yeah.
On the website, it says 100-kilometer radius. Which of those two are they?
Apologize. It's a 100-kilometer radius.
Okay.
Yes.
Thank you.
100 kilometers.
Everyone just breathe a sigh of relief.
Yeah. 100 kilometers that you can drive, so that makes the radius from the center. Oh. We got one down here.
You know, we've talked a lot about the search for life on Mars, microbial, past, present. What happens if we find it, if we can figure out how we find it? And how do we determine, talk about some of the safety factors of manned missions, how do we determine the safety factor part of that, of how humans might interact with that?
Yeah, so this gets into the planetary protection, is that your question? Yeah, so for us and for what we studied, I think that our treatment is that we need to determine the right implementation for doing that. We don't know what the right implementation is right now. And the hope is, and I think that we're pretty optimistic, that we can determine an implementation that will satisfy our concerns about human safety as well as for contamination of the Mars resources. And it's just a matter of finding that right implementation and implementing it correctly.
We can take one more question, and then we got to get to the next one. Anyone else have another one? Over here, can we go, Mike?
I'll repeat it.
Yeah.
I'll repeat.
100-kilometer radius parameter, but isn't it more useful to have a certain amount of resource parameter? I mean, it's got topography, there's
Yeah. Okay. So the question is
area, not or
yeah. The question. Yeah. The question is we're saying 100 kilometers, and maybe it's not like that. Not realistic. It really if there was a big mountain in the way, then maybe you would have a lot less. Yeah. So there.
Or you might be able to go
the idea.
in one direction.
Yeah, and this is the hope is that when we sit down and look at some of these exploration zones in more detail, we're going to have a lot better idea about what are the trafficability concerns, what are the real, criteria that we can use as far as trafficability and movement. And oh no, that we had this ROI over here, but we really can't get there. But for the purposes of this initial thing, it was just a simplification.
Okay, so we're ready to go to our next talk. It's Steve Hoffman, who will talk the ISWIG, which is our ISRU Civil Engineering Group, and get you caught up with that thinking so far. Then we will have I think it's a 15-minute break here. There is coffee out there. We are going to ask, unfortunately the agency can't pay for coffee, so we're asking for donations. If you can, there'll be a donation thing out there, but there should be hot coffee enough for those who need it like me. So anyway, Steve.
So understanding that I'm the only thing standing between you and your coffee. We'll try and keep this simple. We'll get to the mic. Mic's not open. Thank you. I'll try and keep this reasonably simple, and it's going to be I'm going to try and explain more where these criteria came from than the process, I guess, by which we structured ourselves to get to them. Before I forget it, though, and at my age you start to forget things without writing them down, to address some of the recent questions, 100 kilometers radius is based on some of the studies that we've done with these rovers that we anticipate using for human crews. 100 kilometers is just a number that you can work with. That's not the odometer. We realize the odometer is going to be something more than that. And the actual range that you can reach is, in fact, related to how many ups and downs, how many back and forths you have to go through to get from point A to point B. So within a 100-kilometer radius, you may not be able to get to every place in that that circle, that nice geometric device, simply because the terrain won't let you. So don't take that as a hard and fast rule that says I can reach from where I start to where I end is 100 kilometers, I can reach that. That doesn't necessarily follow. It gives you a guideline for which you can look at what are the different places that I can notionally reach with a reasonable expectation given the kind of systems that we're looking at right now. Another question that I heard was how much space do you have to have between a resource ROI and a science ROI? They can be the same place. We're looking for water ice, as you'll see here in a minute. Water ice is a big deal for ISRU purposes for sustainability of the crew on the surface. Water ice is going to be a big deal for scientific reasons. So that you could have one ROI that has a dual identity of resources and science. You could have an ROI that are completely unrelated from each other. Now, one difference between the ROIs for resources and the ROIs for scientific reasons is the resource ones are probably going to be closer to the landing site than the scientific ones. The scientific ones could be at the edge of this notional 100-kilometer radius geometric device that we're talking about right now. The resource ones are probably not. There's an economics associated with resources. The farther I have to go to get something, or the deeper I have to dig to it, or the more I have to process whatever the raw material is to get the stuff out that I want, there's a cost associated with that. And there's a tipping point between how much do I want to invest in the cost to get to that resource and the benefit that I'm going to realize by having it. So resource ROIs are probably going to be closer to the landing site. Resource ROIs are probably going to be closer to the surface. They're probably going to be simpler to get to than some of the science ROIs are going to be. So you can think of it that way. But there's no distinction. We're not trying to make a distinction that says a resource ROI is here and you can't have a science ROI any closer than this. They could be the same thing as far as we're concerned. So keep that in mind as you're thinking about this more. So here's the kind of things I'm going to talk about. I'll try and keep it short and spend more time on explaining why than on how. The science community has a long tradition in picking landing sites for various robotic missions. Resources, well, sending humans is a new twist on this, and that brings a new twist into what the humans are probably going to need when they get there. Now, mention was made of making these missions sustainable.
Those of you who are familiar with DRA-5 understand that in that construct, we were asked to look at sending a crew to a place. We went to different places, and once we went there, we did the exploration we were going to do there, and we left, not to return, presumably. And then we'd move on to another spot. That gave us a means to get to a lot of different places across the surface of Mars. In the construct we're in today, and you'll hear more about it in the next presentation, we've gone to the presumption that we're now investing in the infrastructure at a place from which we will then explore different regions. That's one of the purposes for having a diversity in these scientific regions of interest. If we have, by the time we have invested in that landing site, there's going to be a lot of infrastructure there. There's going to presumably be 2, 3, 4 crews, 5 crews maybe, that will visit that same site. And if the first crew figures out everything that's of interest there, then the second crew, third crew, fourth crew are going to spend a lot of time doing not a whole lot. So we're interested in not only the number, but the diversity of those regions of interest that these crews are going to visit. It means also that we're going to have, or we're going to want to rely on the resources that are there. We call them resources, water being a very good example, that can reduce the amount of logistics we need to bring with the crew each time the crew visits there. And hopefully over time that amount of logistics goes down, continues to decrease over time as we invest more in the infrastructure that we have available. So those are the drivers behind many of the criteria that you're going to see here discussed here, or that you've already seen discussed in the criteria that were sent out. We stood up a group, the acronym was ICE for ISRU and Civil Engineering, to cover a broad range of topics that are associated with that sustainability part of these exploration zones. And our charter was to look at these kinds of questions in order to come up with criteria that those of you who are now looking at exploration zones could take and compare to what you're looking at and tell us whether a place that you're proposing to go will satisfy those criteria, or at least have the potential to satisfy those kind of criteria. This is the group that was set up to do that. I was co-chair along with Rob Mueller from the Kennedy Space Center. We had about a dozen folks from a variety of different NASA centers or other institutions that had a broad range of understanding of what Mars was and what ISRU and civil engineering is, and what the technologies associated with both of those are, or our capabilities are, or where we expect them to go. And so I think it was a good group. I think we had a lot of interaction amongst this group. And if you see anybody on there that you know, you can ask them questions in more detail if you'd like about what we did and how we did it. Just very briefly, we had a rather short period of time to put together these criteria to get them out to you so that you could use them in your considerations for these exploration zones. And in short, we had until the early part of June in order to come up with these criteria. They are a first cut, so recognize them for that. Mention was made of a discussion on Friday. We will ask you to tell us whether these criteria are worthwhile or not. Worthwhile is probably a bad choice of words. What can we do to improve those criteria? We tried to put numbers on them. Those numbers are our current best guess. If those numbers are impossible to reach, or if those numbers are too simplistic, we would like to have that kind of feedback from you. I kind of described this, but let me say it again. In the DRA-5 era, we were looking at 3 different landing sites with 3 different crews. The crew would go there, spend roughly 500 days on the surface, and depart. And there would be no subsequent visits by any other crews. We are now in a case or a situation where the Evolvable Mars campaign is looking at a single site visited by multiple crews, and spending long durations of time at that site. So notionally, or what orbit mechanics allows us to do is to send a crew there and have the crew spend anywhere from 300-ish days to 500-ish days, at that site, exploring that site before they have to leave. One of the things that we are assuming to help make this thing more sustainable, more doable, I guess, is that we've already made an assumption that we will make part of the propellant that the crews need to get off the surface, and we are assuming that the crews are going to get off the surface and return. Part of that propellant will be made from the atmosphere. We know where the atmosphere is, we know what the atmosphere is made of, we know that any place we pick, there's going to be an atmosphere. So that's what we have assumed at the moment for making part of the propellant we need to get off the ground, and that's the oxygen part of a hydrogen or a methane oxygen system. We would like to make all of the propellant on the surface. That would be a goal, but we also recognize that to make all of the propellant, you're going to have a source of hydrogen. Hydrogen is probably going to come from water. It doesn't have to, but if we go to a place where we're going to make all of the propellant, we have to be able to guarantee that we can make enough of that propellant for all those crews to get off the ground and back into orbit. So that becomes an added criteria on picking a landing site. From the crew's perspective, a very important criteria. So it is a consideration that that drove many of the higher level goals, objectives that we set for ourselves, and you'll see that shortly. As I mentioned, for those of you who are familiar with DRA-5, the surface mission, even though we're talking about going repeatedly to the same site, the way in which we would go to or explore that site is going to be very similar to the way DRA-5 described it. So you have a central base, you have a way to drive away from that base, and that part will remain largely the same. We also recognize that by talking about resources now, those of you who are involved in the resource industry here on Earth will understand that saying something looks like it's a good place to go drill for oil or drill for water doesn't guarantee that you're going to find it there. So we deliberately chose the word potential, and it means that we're looking for right now for the best evidence that we have that the resources we're looking for could be at that site. We recognize that we're going to have to gather more data. That data could be orbital, that data could be from the surface, but at some point we're going to have to gather more data to go from potential to actual. And how we get from potential to actual is still to be defined. So a question was raised earlier, how many precursor missions? I can't tell you. I don't think anybody here is going to be able to tell you how many precursor missions there are. But if you come in with an EZ that tells us we need 20 precursor missions before I can decide if I even want to go to a site, it's probably not going to be one that will be given much consideration. If you tell us we need one to verify that the data is there, that probably has a high probability of happening. We recognize that that's something that's going to have to be there. These are the objectives that we had for ourselves. I'm going to talk about the top level one. Top level bullets in this. We can discuss the lower level ones later if you'd like. We're looking for commodities that will help us have an effective and sustainable base on the surface. The highest priority of those for us is water. Water can be used for a lot of different purposes, whether it's propellant. The crew can use it for drinking, that sort of thing. It's also a coolant for EVA suits, and that becomes an expendable. So the more EVAs we want to do, the more water we're going to need to make those EVAs possible. If we get into the idea of plant growth, we're going to need water for those kind of crops to occur. Water is also a good moderator for GCRs and SPEs. So for the crews to have to reduce the radiation exposure of the crews on the surface, water becomes a good way of moderating those kind of that radiation exposure, and it can be used in different ways. We also want to demonstrate the ability to what we call manipulate the surface. That's we bunch that together under what we call civil engineering. For some of the structures that we're going to want to place on the surface, we might want to build a better foundation, for example, to make it a more stable place in which to put, for example, a habitat or an ISRU plant. We need to understand what the properties are at that specific site so that we can do a better job of understanding what kind of surface manipulation we may have to do at that site. Bulk material is another example. Bulk material is another source of radiation protection, or can be. It's not as good as water, but it can be used for that purpose. So if there's a way to bury habitation or areas where the crew is spending a lot of time, that may be a beneficial feature of a particular site. And then the last one is to eventually get to a point where we're not as reliant on Earth for all of the supplies that we need for a crew to live and work productively on the surface. So that's where we get into the idea of growing crops and that sort of thing, and having the materials available at the site or at a portion of the site within the EZ is something that we're looking for. How am I doing on time, Ben? Because I want to, okay. I'm not going to go through these in any detail then. I think I've hit what I wanted to with the objectives. There are, let me at least make the point that, and Paul emphasized this before, there are two levels of criteria that we've had. Threshold was the ones that we want to have. Think of it as requirements. If it doesn't have it, it doesn't work for us. There's a second one, qualifying. Those are enhancements. If you have one of our threshold criteria is having one source where we can find water, whether that's water ice or hydrated minerals, we want to have one of them. If you have 10 of them, you've met the threshold and you've made an enhancement to that because you have more than one, and that improves our chances, or it makes our site more attractive from an ISRU perspective. So when you look at these, think of that difference between threshold and qualifying. The other thing that you'll notice is an acronym in here called TBR. For those of you who are not familiar with NASA speak, that means to be reviewed. We've tried to put, as I mentioned, quantitative numbers on here. Those are our best guess. And we're looking for your feedback to help us understand whether, from your perspective, what we're asking for is impossible to reach or merely difficult to reach. So we're asking for your feedback in those areas. I'm not going to read these words. It's probably impossible to read these words anyway. But let me briefly explain. One of the criteria we put in our call was for 100 metric tons of water. 100 metric tons is a value with one significant digit, but it has some meaning behind it. The vehicle that we need to lift the crew off the surface, and it's a crew of 4, weighs about 35 tons on the surface. About 20 tons of that, between 20 and 25 tons of that, is propellant. And roughly 15 to 18 tons of that is oxygen, and the rest of it is methane. If we can deliver that ascent vehicle dry, we've saved ourselves 20 tons that we didn't have to launch from Earth. So if we can find a way to make that much propellant from a local resource, we've saved ourselves quite a bit. And it's measured in whole number SLS launches. It's not an insignificant amount for the longer term exploration of the planet. If you now think about having 3, 4, 5 crews going back to the same place and needing 20-ish tons of ascent propellant for each one of those crews, you can start to get an understanding of why we're looking for a resource that's measured in the hundreds of metric ton range and not something smaller than that. So we can talk about that, or you can ask me questions about that in more detail later on if you choose to, but there is some basis for picking a number of that magnitude. Now that said, there was this diagram or similar kind of diagram in the criteria that explained that even though we're looking for something that appears to be a large number, it may not be a large number in terms of what we have to do when you put it in practical terms, what we have to get in terms of the raw material that we need to do that. So I don't have enough time to spend on that one. I apologize for that. And then a greenhouse. You're going to see in the next presentation some of our notional ideas of what a greenhouse means or what it can provide to the crew. This is an explanation of where we came up with some of the numbers that we included for crop growth. We need not only water for the crops, but we need some sort of media for them to grow in. Hydroponics is a possibility. We're not ruling that out, but having a medium in which plants are grown is also an option we want to look at. And there are certain kind of materials, raw materials on the surface of Mars that would satisfy that requirement. And this is an explanation for where we came up with the kinds of quantities of those materials that we're looking for. So I think I've covered what I wanted to for now. We're looking for your feedback, as I said, for how we did with these criteria. We recognize that we are not going to be able to validate the existence of the quantities and maybe even the kinds of raw materials that are on the surface based on orbital data alone, but we have to get as close as we can. We're not going to have the luxury of having a dozen precursor missions so that we can down select from 10-ish sites to one site. We're going to have to do as smart a job as we can based on orbital data because that's easier to obtain. But at some point we recognize that actually going to a site is probably in the process of picking that site. So keep that in mind. If you're going to ask for a quantity of how many precursors do I get, I don't know, and I don't think you're going to get anybody here to tell you that number either. It's going to be dependent upon what you're proposing to do and how much data you really need to prove what you need to prove about your site. So that, any questions briefly? Where's...
All right, the question that I have is when we were in the supplemental materials that were provided, there was the talk of that 20 metric tons per crew, and I caught it just very briefly as you were clicking through. The assumption is 5 crews will visit the field station, so we need 100 metric tons of water production capability over the lifetime of that field station, correct?
Yes.
What if, since that's a qualifying thing, there was open to interpretation. If there's less, if there's 60, we can send 3 crews, but it wasn't specified in the material when developing these EZs. So I'm just wondering how big of a stickler are we going to be for 100 metric tons of ISRU water?
It has one significant digit, so 60 metric tons may be perfectly suitable. 120 metric tons may be a requirement. We won't know until we get there. But it's not going to be, we're not going to send 1 crew and then quit. We're probably not going to invest this amount of resources to send 3 crews and then quit. So that's why we put it at 100 metric tons to give a threshold value to the quantity that we need to have. And when we pick the site, since we're going there repeatedly, if our raw material peters out at 60 metric tons, you know, that's probably not going to be a good thing. And so we need to have the ability to make sure that we have that quantity for this longer period of time.
Okay.
Yeah.
Got a big mouth. I'll use this. Are we to assume, are we married to this concept, we're going back to the same place over and over again, or is that kind of still open to discussion, or?
Well, I've been in the business long enough that I've seen that merry-go-round go around a couple of times. So this is the world that we're in now. And these are the questions we are being asked to address now. So that's why you see the criteria stated the way they are now.
Well, hang on.
So
Go ahead.
I think
these are better.
for the next 3 days, the answer is yes.
Understand.
So
I understand we need ground rules to get
Yeah,
the
no,
foundation to
seriously,
start with,
if
but-
we go down a rabbit hole of sort emissions versus exploration, that is not going to do us any good for the process that we've set up.
So the only thing I would add to that is if you look at the history of exploration, and I'm not talking just space exploration, I'm talking McMurdo, start going back. In fact, I was just at Jamestown literally 2 months ago, which was basically a disaster, from a long-term perspective. Well, the one things that succeeded were the ones that essentially did what we're doing on space station, where you're building up infrastructure and you can actually handle catastrophes when they happen, and they will happen, and you have those options. So, I might even go a little further than Ben on that point, but for this week, this is what we're assuming, and furthermore, if you look at history, I'd argue there's probably some rationale in it, if you're serious about being there for a while. Yeah.
And so my answer was perhaps a bit flip, but it's also the history that I bring with me, the baggage I bring with me, I guess. I consider this probably a better way to go because it indicates a more serious perspective on what we're trying to do. If you're willing to invest in a place versus going from one place, if you go to one place and then quit, you also have the possibility of that being the only place you go. You go there once and you're done. I prefer not to see that. If we're now talking in as serious terms as we are now, in investing in a spot and going back there repeatedly and investing in that to the point of growing crops, investing in ISRU, that is at a different level than some of the discussions that we've had in the past. And I think that is an improvement in where we have been. And it is an indication that we're talking about something more serious now than we have in the past. Human Mars missions have always been 20 years in the future. They kind of still are 20 years in the future. But this group is here now talking about, in all seriousness, where are we going to send people? That has not happened before. People have had propose their ideas, but they're on their own, proposing on their own. This is my idea for a good place. That's fine. You can make that case. We're now in an organized arena talking about a process for identifying and studying where we're going to send people. And I think that's an advance on where we have been in the past.
Yeah, I've been around long enough to see it.
Okay, we've got time for one more, then we're going to take a break. Did I see what?
This is a quick one. Given its resource intensity and its risk, why would we be making requirements for agriculture rather than assuming that in 20 years we would come up with a new way of meeting our nutritional requirements? Not that I don't like salad, but...
Okay, I did not have the luxury of staying at a Holiday Inn last night, so I won't claim to be an expert in nutritional science. That said, the nutritionists that we have spoken to have told us that food, canned, packaged, or otherwise, tends to lose its nutritional value after a few years, and we haven't figured out how to make that stop, that degradation in the nutritional value of food stop. So if we're talking about pre-positioning the food that we need many years in advance, and for the crew staying, a year, 18 months at a particular location, I don't think the food science is to the point where they could say that we would be providing the crew with nutritionally valuable food by the end of their mission. And boat rations and saltine crackers are probably not the way that you want to go with for those extended periods of time.
There's an important scientific and philosophical point here to be made, and that is that once we colonize a natural environment, no matter how alien it is to us, we will be altering the environment irrevocably, just as we've done with agriculture on the Earth. So if we're also scientifically exploring Mars, we have to be prepared for the unintended consequences of that agriculture, even aside from the ISRU.
Absolutely true. And what you'll see you'll hear about in the planetary protection presentation is that, well, I'm not going to go there. You're going to hear about that. No, in all fairness, I shouldn't speak for somebody else who's going to make their presentation in the future. But your point is a fair one. And to take it even farther than that, suits leak, habitats leak. As soon as we make the decision to land people on the surface, we have irrevocably changed the surface, whether we go down the agriculture path or not. So that's a tipping point. As soon as a human being lands on the surface, it's a tipping point. And I think that the tipping point in that case is much larger than the tipping point between agriculture and not agriculture. So yes, you will irrevocably change the surface. Whether we change it in a way that makes it impossible to explore further, I don't know. But it is a tipping point. And we're at that discussion step now.
Okay, thank you. So we've come to our first break. We are slightly behind, but your cunning steering committee has built in some spare time. So if we can aim to be back in the seats ready to go no later than 3:20, gives you a little over 15 minutes, we're good to go. But we are going to start promptly at 3:20. Thanks.
So I had some material prepared here, and I'm only going to dwell on things that are sort of new material within this presentation. A lot of it's been touched on some of the previous presenters. My name is Larry Toops. I'm here at Johnson Space Center. I'm in what Ellen Ochoa at START identified as the Exploration, Integration, and Science Directorate. Within that office, we have the group, the Exploration Mission Planning Office, that does some of the reference architectures that she mentioned. Myself and Steve Hoffman here are sort of co-leads within what we call the Evolvable Mars campaign related to surface missions. So that's sort of the context why I'm here today. So I was going to spend just a minute to sort of describe what EMC is. So within the Human Exploration and Mission Directorate, we've had a number of iterations of it. It's now called the Evolvable Mars campaign. But it's a multi-center group of folks looking at specific aspects of a journey to Mars. Again, the latest iteration is called the Evolvable Mars campaign. So I hope as I go through this, I'll be able to communicate to you a little bit of what that really means and what it may not mean. So the title of the presentation is Pioneering Space Through an Evolvable Mars Campaign. Steve touched on it in the previous presentation a little bit. Our concern, at least with our work, has always been what's needed to actually sustain a crew on the surface of Mars, again, for long periods of time. Science plays into that. It's not been neglected in our work the last few years. In fact, we've done some good work, I think. Steve is here, Mary Ann Bobskill, all three of us, and Rob Mueller, are all within this Evolvable Mars campaign team, but we're all members of the steering committee here. So again, we look forward to finding what is uncovered from this workshop and applying it to our work. This, if you want to say, is sort of a mission statement, goals and objective for our Evolvable Mars campaign. This traces back to the NASA Authorization Act of 2010. I've kind of highlighted within this presentation aspects that relate to this workshop. And again, the wording here talks about more sustainable and even indefinite in terms of leaving Earth for extended periods of time. One of the guiding, I guess you'd say, lights in a way for our work is what we've agreed to within the Evolvable Mars campaign, what we call strategic principles for, again, a sustained exploration. Again, I've highlighted three here. I think they're very important to focus on. The first is exploration enables science, and science enables exploration. I think that's what this workshop is all about. And it's a simple phrase, but I think it's an important one, because we've been exploring Mars, again, for a number of years, right, robotically. But we need to come to the point, I think that's what this workshop starts, is where we're leveraging that robotic experience and expertise to our exploration of the solar system related to our human exploration beyond low Earth orbit. The second one I've highlighted is what's termed near-term mission opportunities. but with a defined cadence of compelling and integrated human and robotic missions that provide an incremental buildup. So the idea behind an Evolvable Mars campaign is to look at options. We're not coming up and we're not going to try to describe to you. We're going to give you some metrics, like in the last case of Steve's comments, something to go by. But we want that to inform us to where there's actually a cadence of an incremental buildup that's possible, so that we can identify all the different options that our group internally identifies within HEOMD, but also the Science Directorate. Other outside organizations that, let's look at it in a different light. Food growth was brought up in the last presentation with a comment. Okay. These lights are crazy because it is like being in sync. I can't see anyone, but I can hear that. So the idea here is that maybe we're given a mission to look at that doesn't include food growth, right? So one point to be made is that we're not looking at a specific implementation, but something in terms of guiding principles, some mission objectives, some ground rules and assumptions that allow us to make calculated and reasonable decisions as we leave low Earth orbit, okay? The last one here is, again, a resilient architecture that features multi-use evolvable space infrastructure. An example of this, within our EMC right now, in terms of habitation, we have some folks looking at what I would call Skylab 2. How do you use the assets of the Space Launch System we're developing, and how does that impact a campaign leaving the Earth and eventually arriving at Mars? That's an example of using an infrastructure that may be already in place or that we may be developing that we'll use in a certain approach. This is kind of an important chart, even though it's very busy. I tried to simplify it a little bit with some headings. So within our EMC team, we look at the breadth of what's involved in terms of an Evolvable Mars campaign, an evolvable campaign that gets to Mars. But we also look at depth. So you see we do campaign analysis, timelines, and actually identify some decision needs. We do mission operations development. We do element conceptualization and design. Then we do a capability needs analysis. But as you can see, going from left to right, the bottom and the top one in particular inform decision makers, inform strategic planning that's going on within the agency and even outside the agency. So that is one of the products of our EMC. The two that are in the middle are where mainly Steve and myself and a few others like Rob and Mary Ann are concentrated in. We look at options and what are the concept of operations involved with that particular option. And then an element such as a pressurized rover. What kind of capability is required of that rover? We're not doing a fine endpoint design of it, but we're uncovering enough that we can actually maybe dig up some nuggets of goodness that'll actually inform the campaign analysis. So it's across and it's also down in some ways. I've highlighted here what we expect to try to get out of this workshop is within that mission operations development. Again, validating is an exploration zone a legitimate way to look at introducing human exploration. It includes some other things such as the destination operations themselves, but basically within the EMC, that's where most of our expertise that's represented here at the workshop is in. This was touched on, and again, I think in Ellen's comments, actually John Grunsfeld's as well. 3 phases, Earth reliant. I'm not going to probably repeat too much here, but eventually what we're really focused on within this workshop is Earth independence. In other words, what are some of the things that are related to a legitimate site selection that was touched on in Steve's. It was also touched in Paul Niles' presentation as well. What allows us to become Earth independent, knowing that with ISS in the Earth reliant stage, we're going to use ISS to do, again, human research. We'll actually test out some technologies. Food growth was brought up a minute ago. We do have a veggie unit on space station. So we may learn quite a bit from that. But the really next step after that, within the next decade, is what we call this proving ground. That's located pretty much in cislunar and what we call deep space. The operations may get a little more complex. The autonomy of the crew may increase. The technologies that we demonstrate within that context will probably start to touch on the sustainability aspect of, again, that Earth-reliant or Earth-independent stage. A few of the proving ground objectives that are more specific touch on things that are through analysis in the flights themselves, looking at the solar electric propulsion system to move large masses around, the lunar distant retrograde orbit as a staging point to accumulate things that may eventually be moved to Mars, the use of the SLS and Orion in deep space as well. An important one to us within our work, again, how do you establish a habitation system that allows for long duration stays in deep space that cuts down on that resupply chain that we have currently in ISS. Those are pretty much, very much related to that one that says operations with reduced logistics capabilities. But also from an operations standpoint, EVAs in deep space with sample handling, integrated human and robot mission operations, maybe start to try to test out some operational concepts that may help us in the vicinity of Mars, as well as maybe on the surface. I leapfrog again to this becoming Earth independent. So initial human missions might include tech demonstrations for things such as in situ resource utilization. Steve touched on those. Building infrastructure, again, the civil engineering piece of all that touched on that. Something that we're all aware of now, 3D printing or additive manufacturing systems locally in situ. We mentioned growing food before. Even human social engineering. And in part of that is actually the humans performing Mars science. This was also mentioned, returning to a single site. So we talked about exploration zones. We talked about EMC. One of the things I'd like for you to take away from this is Mars Surface Field Station. Currently, that's our thinking. We're looking at, this is getting you to the surface of Mars. This is the work that Steve and I co-lead, where the architectural approach in that, it's like a three-phased approach. Again, it'd be overlapping, so it's not that it's going to be a definite stop and start to it, but it's a two major milestone approach with these three phases. At the end of the first phase, which is the one that we've really looked at pretty much in detail last year, is what we call emplacement. So that by that time on the surface of Mars, you can enable a crew of 4 to be Earth independent for 12 to 18 months. Okay. What we're currently looking at, and what this workshop will help inform us to, is what we call a Mars surface proving ground phase. And during that is where you can see the notional picture up at the top. It's very similar to, like Rick said, an Antarctic field station. If you look at pictures from McMurdo, Scott's Hut was established in 1902. Human permanent occupation of McMurdo didn't really happen until 1955. So there's a period of time that's going to be required here. It's not going to be a short duration of time. But that Mars surface proving ground phase and that Mars surface field station will allow us to test and demonstrate things that are related to what we call known unknowns as well as unknown unknowns. That eventually leads to a point where you can say, we've reached our ultimate goal, an indefinite stay is really enabled here. So this is a picture again of McMurdo 1955. And again, it just sort of, there's really an analogy here between the the surface field stations that we use on Earth. Again, they bring the basic tools of research. So you'll see within our work that we provide electricity to communication. All those capabilities are needed. to provide access to the environment. We need to provide logistical support while the crews are there. But they bridge the natural environment and the research laboratories. So in our estimation, in our approach for at least this fiscal year, the option that we're looking at is the idea that the field station combines both of those. You've seen this already. I'm not going to probably go over it too much more, but what you see on the upper right is we've done more detailed work on what that Mars surface field station, you'll see that in a second. So the major results to date within the EMC, this is overall, this doesn't just focus on our Mars surface work, is regardless of the vicinity destination, common capability developments are required. The ISS does provide a critical Mars mission capability platform to test and demonstrate things. Lunar DRO is efficient for aggregation and potential refurbishment. Deep space habitation serves as an initial starting point regardless of implementation. And that actually Mars Phobos Deimos as an initial Mars vicinity may spread out development costs and meet policy objectives of the Mars vicinity. So in summary, what we tend to do with this, after this workshop, is incorporate the results of it. The second bullet here also touches on what Paul Niles described in his presentation, their final report, as well as Steve's final report within IceWig. Just released about October 5th. I would suggest that you look for this document out there. It's called Pioneering Next Steps in Space Exploration, and it does a lot better justice than my few minutes here to describe what we're after here. So what we've done, and I'm going to have some disclaimers here, we've had a group, mainly through Mary Ann's hard efforts, that the goal of the workshop here is to help us validate an exploration zone approach. But what we've tried to do is do a short video here, short animation, to sort of describe what we see it as being, at least from the human exploration part of it. And then keep in mind that what you're seeing here will actually be updated as a result of the workshop today in our work during fiscal 16. So I hope you enjoy it. Some of the things depicted here about a kilometer separation. Thank you for your attention. Thank you. Hey. Oh, you want to take any questions? Okay, any questions? Please. Thank you. Okay, the question was, is the video available? This video was completed last night about 6 p.m. So what you saw is for viewing only, distribution not allowed, but hopefully not yet. It'll be in a few days. So it is, and again, we've all heard the inspiration. Okay, we'll see what we can do. We've all heard the inspirational music and the animation, but it really helps depict that interaction of crew on the surface in an exploration zone. Yeah, John.
You know, I loved you starting out with the Mike Wargo exploration of science. Science is exploration. And then talking about the robotics. You know, one thing that, you know, is one of my soapboxes is that there is no such thing as robotic exploration. Robots never discover anything. It's all human exploration. You know, the robots are just a tool. You know, if we could have sent, you know, planetary science to Mars now, we would have. We can't. We send our tools. But that's sort of an adjunct to the kind of thing I think we should all use as a communication tool.
Correct. Yeah, I agree. Any other questions? Okay. Okay. Next speaker. Right. Oh, sorry.
So in the video, are we looking at what the base would appear like after, like during the 5th mission, after we already in place a lot of infrastructure?
Yes, we talked about it, Steve and I. So these are notional images because we really haven't worked out how does all that stuff get assembled. But it represents the notion of a Mars surface field station after 2 to 3 crews at least. Yeah.
All right, thank you.
Yeah, sure. Oh, you want to add something, Steve? Go ahead.
But recognize that we are looking for a place where that can happen eventually. So we have to be able to account for all of those pieces in more or less that configuration when we pick the spot. So even though that represents what it would look like after the 3rd or 4th or 5th crew is there, we need to have the spot where we can accommodate all that from the time that the first crew arrives. That's part of the selection criteria.
And one thing I'll will note, we're actually looking at what we call logistics to living concepts, where we turn that logistics module into another thing, such as an astrobiology lab. You saw the plant growth test and demonstration facility. So the idea is not to deliver additional infrastructure if it's not needed, if you can reuse what's there.
Okay. I hope you can hear me. I don't have a movie, unfortunately, so we're going to go back to the old technology. Just a few slides here. Viewgraphs. Not quite. We want to talk about current data capabilities. We also want to talk about the limitations and what we need to do in the future for what we think are many of the objectives that we ultimately want and need to pursue in order to select a landing site. Fortunately, we have time, but we can get started with the information that we have today. So I'm really representing 2 kinds of activities here. One is the current orbiter capabilities, and to talk more about that, the 3 orbiters that are still operating and able to contribute here. I'll talk about some of the new missions that have just arrived at Mars as well. But these have been the workhorses for our robotic program. And yes, the only difference between robotic and human exploration is where the humans are. And to this point, we've been on Earth. One day, perhaps, we shall be on Mars. So these are the capabilities that we have, and these are some of the instruments, in particular on the Mars Reconnaissance Orbiter, which has sort of been the workhorse of many of the robotic mission landing sites that we've talked about. Now, one of the reasons that MRO has been the workhorse is because of its ability to see things at higher resolution, spatial resolution on the surface from its 300-kilometer altitude orbit. And here you see that as compared to the previous missions, including some of those that are still operating, like Mars Express and the Odyssey mission, that MRO has been able to push some of these observations in the visible, and the near-infrared. Many of the mineral signatures, hydrated mineral signatures that we see, are most easily detected in the near-infrared, and so that's part of the emphasis. The percentages that are in some of the bubbles there are the parts of Mars that we've covered at different resolutions. And you can see that as you go to high resolution, that MRO, even though it's returned over 250 terabits of science data alone over its 9-year in Mars orbit, that we're still just covering a few percent of the planet. Now, it's not a random few percent. It's targeted based upon the lower resolution data that we get. You need to keep this in mind as we go forward in talking about coverage and what data sets would be most useful for advancing our understandings of the landing sites that you'll be presenting here over the next few days. Just to give you some idea of the progress that can be made here, this is showing you right now there's several customers for landing site certification and characterization, including the 2020 mission, the ExoMars mission, and we just now are finishing up for InSight, which is about to launch in March of next year. We still look at some of the MSL areas and helping with the operational planning of that, but also to help with the science synergies of things as well. The point here is down there on the lower right, where we're talking about 200 landing sites, targets in 14 months, and that's about 7 per 2-week planning cycle for MRO. And the purpose of this is to say, if you ask us to cover a 100-kilometer size radius ellipse, it's going to take some time to do that. In fact, as you down select, it takes longer, because when they're scattered all over the planet, there's more opportunities to see them from the orbiter than there. So when you think about what are the data sets that I need and would like to see, this is telling you, be realistic in what you want and be discriminating. So the more information you can give us about what's important, the better. This is just to give you an example of what we've done for the InSight. This is the site that they will recommend for their landing in September. And it has not yet been fully approved, but you see the coverage that is here. Now, we are talking about something different. For the robotic missions, we are trying to certify this entire air ellipse where the lander might sit down, the safety of that zone. And so this is different than what we're talking about for the exploration zones, where the landing site is actually much smaller than that. And so there are other capabilities. And part of that is to define what we mean by prototyping and to go from this period where it's just certification to one of, no, it has to do with the elements that are all connected here. So to remind you of some of this, here's our classic exploration zone that you've seen several times here. And I'm just going to put on here the 2 resolutions of the MRO imaging systems, visual imaging systems. High-rise is down there about 5.4 kilometers by about 15 or more, depending upon our ability to control. And CTX, which is lower resolution, but covers much more. Now, most of the planet has been covered with the CTX resolution, and for the high resolution, we're still talking about a few percent. And this is true for the mineral mappers as well as for the visual imaging systems. So, contributions by the new Mars orbiters. MAVEN, which has been in orbit for about a year now and is just transitioning from its its prime mission, and it will transition from its prime mission in November to an extended mission prior to the senior review process next year for all of our operating Mars assets. Trace gas orbiter, I think the launch period here is actually March 14th. Is that right, Jorge? I think I may have gotten the InSight one mixed into this. It has several instruments focused on trace gases in the atmosphere. It does have a neutron epithermal spectrometer that is looking, and here the footprint, hopefully this is a collimated one. Typically your footprint for these kinds of instruments is the orbit altitude, typically 400 kilometers. And here, by using a collimated system, they hope to be able to shrink that, to oversample and to get that down. This is still very large on the basis of what we want to consider, for instance, for finding resources. So what's missing? Well, all these orbiters are a little long in the tooth. MRO is the new one, and it just celebrated its 10th anniversary of launch. So making sure that we have those capabilities for the future is one of those. Detection of ground ice in the top meters or so. We've had sounding radars on both MRO and Sherrod. Sherrod on MRO and Marsus on the Mars Express spacecraft. And as sounders, they're probing into the surface. The resolution, if you will, the return cell on the surface can be pretty broad, a few kilometers and such. And we're sort of blind to that first wavelength of material into the surface. So we're looking for something that is more accessible in terms of the resources, and there's an important science question to that as well, as we'll talk about here in a minute. There's also the issue of the continuity of ground ice. Are things rather contiguous? That is, there's a large deposit that extends for several football fields or such, or is it more sporadic? Sometimes when we detect something in a footprint, which is pretty broad from orbit, and we try to look for it with our rovers, it's actually hard to find because it may be concentrated in thin veins of material as opposed to something more evenly distributed through material that could be easily mined. Phobos and Deimos are also targets for in situ exploration and operations by humans, although we're not looking for landing sites on there. In our considerations about the next orbiter, this is an element that comes into play. So for that next orbiter, Steve has already walked you through what the ICE working group has set up as prospecting objectives and such, and those have been provided to a new group. The MEPAG has organized a science analysis group to look at the next orbiter. We call that NEXAG, and define not only the science objectives to complement the resource prospecting objectives, but also to look at measurement approaches and see if there are synergies between them, which makes it easier to fly with reasonable payloads into those. So for the resources, you've seen some of this. It's primarily water. The type of water, whether it's hydrated minerals or shallow ground ice, and again, the accessibility, and it's difficult to quantify mineral deposits from orbit. So we're not kidding ourselves about there's going to have to be some follow-up exploration and confirmation of that at the surface itself. But where to look, where do you put those landed elements is what the orbiter can direct. There are other parts, including diurnal coverage of things. Our orbiters have tended to be solar fixed. What happens during other times of day is we haven't got an extensive data set. That's true for the atmosphere and for volatile changes that are on the surface, such as these recurring slope lineae and such. So those are the resource objectives. Here's the NEXAG membership. Bruce Campbell at the Smithsonian Institution and myself are co-chairing that. And it is interacting with an orbiter study team at JPL that's been looking at, okay, how do we package various things? What's the range of mission concepts that we might use? One of the very exciting possibilities is the use of solar electric propulsion for a Mars mission. That helps you take what otherwise is fuel and convert it into payload and take it into the Mars system. It also gives you a geometry that makes things like looking at Phobos and Deimos as you're spiraling into low Mars orbit possible. And so your payload can get serendipitous science on those, even if it's focused on sites on from low orbit on Mars. The science objectives, ground ice deposits to better understand the global inventory and atmospheric exchange today and how ice records might tell us about climate change on much longer time scales. First, the obliquity variations of hundreds of thousands to millions of years, and then even back further than that. One of the new things is to follow up, of course, on our discoveries about these recurring slope lineae, which are possible brine flows, salts identified associated with these, and to link these to the properties so that we understand the mechanism and look for what might be the source of that water. Measure winds, characterize dynamical processes, both as a means of just defining the environmental engineering environments and to take a look at processes with extrapolation to the past. We have models. We need to verify those models, validate those models. characterize the currents and timing of major environmental transitions, our record has shown that in ancient Mars, there's a huge diversity. There were many kinds of water environments that were present at that time. They've left different signatures in terms of the mineralogy and the stratigraphy of the surface. And trying to understand the timing of those, the duration of those, is important to our interpretation. And then with solar electric propulsion missions, yes, you can do some investigations there. Needless to say, there's a high degree of synergy between these. You've heard the similar themes in both the science and the resource prospecting of shallow ground ice, hydrated minerals, where does that lie? What is it at the higher resolution scales that we need and want to go to? That's good because that means we can take instruments that address multiple objectives, single instruments, and those then can fit better into the resources that we can apply to this. Launch in 2022 is, by this group, is felt to expedite providing information early enough that you could actually do things, and progress on the landing sites. If you're launching in 2022, then it's 2023 before this data is coming back to you, and I would like to make progress faster, but that's our next step and our next window to do that. I want to pick up a point that I kind of went over very quickly before, which is in addition to the telecommunications support, if you look up there in the bold at the top, there's also the possible preparation for future sample return, either as a demonstration of the rendezvous and capture that would be needed to take an orbited cache and to capture that and show that we can do that in Mars orbit, or to actually do the return itself. And I think we'll hear more about that later. Since sample return is the highest priority from the decadal survey, not only for Mars, but for solar system science, this would be an exciting prospect. Okay, let's finish up here. And this is showing you that, once again, we want to improve the spatial resolution. And this is what we think the next orbiter could do within the reasonable quantifications of these. And to push this in many directions. For the shallow ground ice in particular, we have to go one more step. And we think the way to do that is using the polarimetric synthetic aperture radar capabilities, where you're actually imaging across, so you're getting high resolution. You're also probing that shallow atmosphere and such. So in these measurement approaches, visible imaging, presently we're at 30 centimeters per pixel. We think within the same size envelope of resources, you could do at least a factor of 2 and perhaps 3 better than that. The polarimetric synthetic aperture radar, and let me emphasize that we're talking about capabilities here, measurement objectives. What the instrument is the future of is the subject of a future science and resource definition team, and ultimately an open announcement of opportunity competition. Shortwave IR mapping, again, this is where the hydrated mineral signatures are. Long-wave atmospheric sounding. One of the issues we've had is that a lot of our measurements are difficult to make in dusty atmospheres, and Mars can be a very dusty atmosphere sometime. But there are techniques, if you go to longer wavelengths, microwaves, a millimeter, that let you do that. So that lets you see things without the dust, but you also have to see the dust because they're all intertwined and connected physically. And we've got a long record of the wide-angle camera looking at weather and surface frost. We've talked about this resolution and such. So the capabilities that are being considered are all the way from what I'll call an MRO light, chemical propulsion kind of mission, to things that use commercial solar electric propulsion. And then if you use the things that are being developed now for instance, for the ARM mission and such, that there is even more capability there. This whole range of things is, the space is being examined even today, and looking at different prospects for how these capabilities could be used. This next orbiter SAG believes that you really need this solar electric propulsion to be able to do this multi-function capability. So what are we looking for here? We're looking for the next SAG in particular is right now they've got a draft that's in review. And their report, we're hoping to release that report in mid-November here. We are interested in this workshop and your experience about the things that we might need in trying to characterize and ultimately to select a landing site for humans to explore Mars. In the near term, the MRO project is interested in what data collected in the next few years would make the greatest difference in making an advance using the data that we have and that we can collect before, say, the next workshop that could be utilized and studied to help inform us about landing site capabilities. Remembering that there's some missions in line ahead because they're going to be going to Mars earlier, and we need to finish those things. But depending upon where the sites are, if they're scattered about Mars, and as you saw from the map, they're scattered almost everywhere at Mars today, there are opportunities to pick these up. In the meantime, MRO and Odyssey and Mars Express, and we'll be looking scientifically at new places and new sites. My prediction, and it's just my prediction, is that the site that's going to win the competition may not even be on our chart today. We've got lots to learn about the planet and so forth. So this is what we hope to get out of it, and I'm going to take questions now.
Rich, for this next orbiter, what if it's SEP, what is the timeline? How long does it take to get to Mars, and how long does it take to spiral down into a low orbit?
Yeah, those are options that you have with SEP that we didn't consider before. You're not locked to a particular launch opportunity as we presently are. Excuse me. So we're expecting that it could take on the order of a year to get to Mars, and then the spiral down could take another few months. We're hoping that in low Mars orbit, the specification for this orbiter is that it lasts for 5 years in that low Mars. Did I say Earth? I meant Mars. Low Mars orbit. So now one of the things that it also lets you do, solar electric propulsion, is it lets you actually change the orbit plane so that you could have a mission that is looking at the diurnal cycle by watching different times of day for particular sites. And then you could move it such that you're looking at a solar fixed time to intercompare different seasons and such. It takes a few months to do that from those two kinds of orbits and such.
Yeah, and doesn't that have to be done in a very high altitude? So you wouldn't be changing the plane once you're down at 300 kilometers.
No,
right?
actually you can do it when you're down low, but it takes longer to do that. So the lower the altitude, if you're already in a low altitude orbit, then it would take several more months to accomplish the change. But even that could be interesting in that you're getting different views at different times of days of objects on the surface. Jim?
Yeah, quick question on laser altimeters. So obviously from a site selection point of view, site characterization, et cetera, there have been huge developments since MOLA, which flew a long time ago. We have a laser altimeter in orbit around the moon right now, 6 billions of shots, 6 years. It has 5 shots, and we have technology on Earth and other places where we can do up to probably 15. So this might be a really interesting thing for characterization of landing sites. From a roughness point of view, you can get slopes all over the place, et cetera. So just something to keep in mind.
This group had several presentations from some of the capabilities that are still evolving and such. And I want to point out this line right here. These proof of concepts, that's really what we were looking for. Are there things that we feel confident could be developed for a 2022 mission timeline? There's quite possibly other things. In fact, we were presented some very interesting concepts. If you have solar electric propulsion, you also have a lot of power, which opens up the kinds of instruments that you could have potentially as well. We didn't think we were ready to say that you needed to wait for those kinds of developments and such. We wanted to make sure that there was something that could meet an early 2022 development timeline, which means getting started in the next couple of years. Jerry?
For your SAR, besides the 15 meter per pixel resolution, do you actually have a minimum ice concentration or ice thickness that is detectable with it?
With the polarimetric radars and such, it's easier to see ice slabs than it is if it's pore ice. Then we're going to have to rely upon the temperature, ground temperature measurements as indicating there's something different about the composition of this surface. The hope is between the two, between the synergy of the payloads, that you'd be able to get an idea about that. What we're also really looking for there is just how contiguous, how continuous would an ice slab or an ice deposit be. We know they're there in that 30 to 50 latitude range. Impacts have exposed those to our high-resolution imagers. So it's a matter of, yeah, if it's mixed, rock and ice, then it's going to be more difficult to pull it out. Yes.
In the context of a
Yes.
landing site characterization, how would that be impacted by having a faster telecom relay back to Earth? Would that, or is it really fundamentally limited by orbital mechanics in a situation like that?
This orbiter would be taking advantage of advanced capabilities we think are already in place. That is, the capability of returning here would be maybe 3 to 10 times more than MROs, and we're still going to be limited to that few percent coverage with that if we go to these higher spatial resolutions. Every time you double that resolution, the data that needs to come back to cover the same area is a factor of 4 geometric in that. So opening up that pipe is really important. And if there are new capabilities that can be applied to that, great. That's really going to help with these kinds of things. So even with this next orbiter, you're not going to get contiguous coverage of all of Mars at a meter scale. That's still not quite in the cards. But we don't need that. We can be specific and we can pyramid our observations so that you find interesting things at the lower resolutions and you focus in. That's what we're doing now. Any others? Yes, Joe.
Thank you, Joe Michalski, PSI, and NHM London. You'd mentioned that, okay, so the solar propulsion may allow for you to have more power in Mars orbit. Have you considered sort of wacky ideas, things like active infrared remote sensing, things where you could sort of access that sort of 3 to 6 micron wavelength zone where you have organics and things like that, where in a passive mode it's very hard to sort of measure anything there because you have downwelling radiance and all sorts of problems. But have you considered sort of off-the-wall, sort of crazier ideas?
Well, we didn't think some of those were off the wall. They just seemed a little bit out of reach. We talked about, for instance, a wind LiDAR or a water profiler that could be very precise about where that water was near the surface. One of our issues now is our typical remote sensing techniques can tell us within 5 kilometers or a kilometer at best, and that's not good enough if you want to study exchange with the surface. It gives you something that you can use as a model boundary condition, but we'd like to do better. Some of the active devices, though, just in particular the water profiler and similar ones, seemed like they were just a step beyond this development cycle. But I'll again just point to this, that these were proof of concept, and the next step would be to get, as the spacecraft capabilities are mapped in a more specific way. That is, now you can do trades between, can I wait? Can I do that? Where do I put my margin? Do I accept 5 miracles or just 2 miracles, in my instrument development? And those things will need further definition of the mission concept before you can do that in a useful way. There is stuff there.
And just a quick comment. I think one thing that concerns me is that as humans, we always want to improve, but better is the enemy of good enough. And HiRISE is, in my opinion, an awesome experiment. It's been conducted nearly perfectly, and it's really useful for scientists. And just more coverage might be better than less coverage at higher resolution in some ways.
That's a trade that we have to make. There was some push to go to and consider even higher resolutions, but there are limitations on the spacecraft as well. Keeping it stable enough to get those kinds of resolutions back. Okay. One more?
Yeah, Jake Bleacher, Goddard Space Flight Center. I'm going to follow up on what Jim was getting at about the topography and surface roughness, and maybe also what Joe was touching on. The point about finding the ROIs that are of interest to ISRU and science is important, but then making sure we can actually get to them within such a broad exploration zone is also important. So we have things like the HiRISE experiment, which is now able to make very detailed DTMs. From those, you can start deriving things such as the roughness and trying to get at the characteristics of the terrain and whether or not they can support more than just the MER and MSL size rovers, but that the rovers we're talking about the humans being in. So coupling future orbiters with rovers such as Mars 2020 seems like a great way to maybe push our risk envelope a little bit and start seeing if we can use the orbital assets to identify terrains and really start to map out navigable paths and then test those paths with the rovers that we have on the surface as we move forward in prep for a human-sized rover, which is much bigger. So I just wanted to kind of make that point.
That's right. There's a scale that you can help with the operations, and traverse planning seems like it would be more important for evaluating an exploration zone where you're trying to estimate times and travel times between places and how much time you would spend there. You can get a lot of information from stereo on these missions, and all these missions would have that capability. And that's at a scale of maybe a meter or maybe tens of centimeters if we go to the higher resolution here. You still use the altimetric things to tie those points down and such. And I think you're arguing that if I went even further, a step further, there's a major step up in your spacecraft capabilities that are required to help support those. And maybe that's within the cards there. Okay? Yeah.
So first of all, we have the whole workshop is being broadcast on Ustream. We do want to, and we really welcome everybody on the internet that's joining us. We want to make sure you realize that we've had to take our chat function down. We're having a problem with it. We will figure out a way to receive inputs and questions that way, and we'll have that ready in the morning. So just want to make sure everyone knew that. Thank you.
I'll just stand here. Sure. I think they want to use it for the recording. Oh, they do. Okay, sorry. All right, good afternoon. I'm here to talk about selecting Mars landing sites from the perspective of the folks who are actually going to have to go there. And I'm starting with a shameless plug for my friend Dan Durda, who did this art. All right, there are a lot of immensely cool places on Mars. Just a couple of examples here. But when you ask the crew which one of them they want to go to, you will get the following answer suitable for public consumption. It's all good. Which is a very positive term for we don't care. And we shouldn't care, right? We decide what we're going to do on Mars. We make objectives for the mission. It's the job of the crew to go there and carry out the mission to make those objectives happen. The details of the place, the identity of the place, not really relevant to us. So we don't care where we go on Mars. In fact, if you ever in the future get a crew rep who, bangs their shoe on the table and says, we absolutely must go to Chrysi Planitia, we must go there, it's time to give Ellen a call. You met her today. She's a nice lady, and say, can we please get a different crew rep? Because seriously, it's not our business where we go on Mars. And that was sort of my reaction when I was first approached to come and talk to this group about where we go on Mars. We don't care. But then I was asked to remind them about some few things that we do care about, and that is safety and operability. So we don't care about the identity of the site, but we care deeply about whether the site is going to kill us and whether, having got there, we can do any work. So that's what I'm going to talk to you about today. This should go very quickly. There'll be plenty of time for questions, and maybe we'll get ahead of schedule. So, question number one, safety. Is the site going to kill us? We're very keen on this, and let's talk about a few aspects of sites that could potentially kill us. First thing that leapt to my mind was high latitude. Now, I know we're not considering sites anywhere near this white patch. But when you get far north and south, you start encountering some problems. First of all, if you have orbiting assets, such as communication satellites that are in low inclination orbits, you can't talk to them very well. If those orbiting assets include, for example, your Earth return propellant, you really want to have that be accessible from where you are. And of course, if you're at X latitude on the surface, you can't reach orbits less than X inclination. Mars is smaller than the Earth, but it turns in 24 hours, and you get a little ascent boost launching to the east with planetary rotation. You go to high latitudes, you get less than that. Now, you say, well, it's just a couple hundred meters per second. Is Tony Antonelli still in the room? He's one of our shuttle pilots. Just a couple hundred meters per second underspeed in your ascent burn is a terrible day. Okay, it means you're probably coming back down. So we really want that planetary rotation boost. Emergency departures back to Earth, if you think you need to get back in a hurry. I know that planetary launch windows forbid that most of the time, but if you're in a high latitude situation and your orbit plane that you launch into is very different from the ecliptic plane, that may restrict your opportunities because it takes more propellant to do that plane change. Finally, raise your hand if you're an ANSMET veteran. Yeah, okay. Antarctica, things break. Even things that we use on Earth often in harsh conditions, you take them down to Antarctica, it gets really cold, and they break. Check the fine print on your iPhone sometime if you think that your modern technology is going to save you from this. It's not, right? Your iPhone loses its surge at about freezing. So if we go to the polar regions of Mars, which are just vastly colder than even the polar regions of Earth, we're signing up for a lot of problems with the equipment that we take with us, almost all of which is going to be important for our survival. High latitudes have a bonus, which is bad lighting. Okay, in the winter, high latitude, there's just not that much daylight. This is bad for landing. Now, I was in the other room when Ben said it, so I didn't get to throw fruit at him, but I'm going to do it now. So Ben said that landing is not that big a deal, and this is a common conclusion people have about work that someone else is going to have to do. Landing is a huge deal. It's next to taking off, it's the most important deal of the whole mission for the crew. That's the only things we care about. Not killing ourselves on landing and then being able to take off again when we're done. That's really it for the mission for the crew. That's what we're really worried about. And those are, seriously though, those are very, very high risk endeavors. We're going to be okay at landing, although I'm thinking about space shuttle. You know, we had to land that on a runway which was the size of a couple hundred meters, and actually the runway itself was only 200 feet wide. But we had radio nav aids on that runway. We had GPS. We had all sorts of goodies that we're not going to have on Mars to make that landing happen. So landing is a big deal, and doing it in the dark, we don't want to do. And if you're driving rovers out to your science sites or to your in situ resource dump or to your ascent vehicle, everything done in the dark gets harder. So great, we'll go in the summertime. High latitude has lots of daylight in the summer, but even then, the sun is low. ANSMET veterans, there's a lot of glare, and any surface irregularities are going to make long shadows and big areas of darkness. So high latitude, in our opinion, is bad. Now, asterisk fine print, I did get a chance to look at some of the preparatory material for this workshop, and your high latitude is about 50 degrees. Okay, my high latitude is above the polar circles. So your high latitude sites are still okay, but 50 degrees, I used to live in Seattle, that's 49 degrees on the Earth, which has less of an axial tilt, so the seasonal adjustments in lighting are different. And even at 49 degrees latitude, the winters are kind of dark, and the summers are kind of low sun and glary. So 50 degrees is probably near the boundary of where things might start getting difficult from a latitude perspective. Right, next, Mars is famous for its dust storms. They are not as bad as shown in The Martian. Unless the wind is going really fast. John talked about rho v squared. Actually, there's plenty of v squared. It's the rho that's low. But we hate dust, right? It's not going to blow your ship over. It's not going to throw pebbles around at you. But it's horrible for landing if you're trying to land the dust. It's bad for your airlocks. It's bad for your suits. It's bad for all your mechanisms. It's bad for your solar panels. It's just a bad thing. So if we can land in a place that is less susceptible to dust storms and doesn't have a lot of free dust around to get mobilized by our activity, that would be a good thing as well. Next, We do not want to land on this. So boulders, big surface roughness, very bad for landing and bad for driving rovers around. Definitely a safety hazard if there's a lot of surface roughness on that scale. And steep slopes are kind of a worry as well. You wouldn't want to try to land a spacecraft on that, and you certainly wouldn't want to try to drive on it. One other consideration is altitude. And in my opinion, altitude is kind of a mixed bag. Low air density has some bonuses for us. They're just sort of discovering now in some experiments done at Kennedy Space Center that if you're landing on a jet, which we're going to have to do, we're going to have a big heavy habitat, airbags is not going to cut it, parachutes is not going to cut it, we're going to have to land on a jet. And if you're in a dry substrate with sand and rocks, that jet digs this big hole that you then land in and tip over, and that's embarrassing. Lower air density is going to let that jet expand a little more. It's not a huge difference on Mars, but the air density is like a factor of 10 lower on the top of those mountains than it is down in the lowlands. It's a big deal. So low air density reduces that jet confinement and might reduce that the tendency to dig holes. And also, dust can't stay in the air very well if the air is very thin. But low air density also has some cons. If we're trying to reject heat from our habitats and the air density is down by a factor of 100, yeah, it's cold outside, but you still got to get out, transfer all that heat to your atmosphere to remove it. Thin air makes that harder. And if you're using any aerodynamic deceleration for landing, you know, like a drogue chute, and the air density is down by a factor of 10, that makes that much harder. So I'd say mixed bag on altitude, but I understand the study group here has some guidelines on altitude anyway. All right, so for safety, the summary, landing and working on Mars is going to be safer if we're not at high latitude, if we're not in a really dusty area, we don't have a lot of big rocks, and we don't have a lot of steep slopes, and high altitude we'll talk about. So that brings us to operability. Can we work there? Interestingly enough, the thing that prevents you from doing work in space is paying attention to safety. Really, it's the biggest driver that prevents us from getting a lot more done is we have to worry about safety considerations. So interestingly enough, the constraints on operability are basically the same list as the constraints on safety. That is, the safer and more temperate the landing site, the more work we can do there, the less time we have to spend making sure that we're going to be safe, and the less time we have to spend maintaining systems that keep us safe in an adverse environment. So again, high latitude, not so good. Dust storms, very bad. Big boulders, steep slopes, high altitude, the jury's still out. And interestingly enough, these are just about the same considerations that you have for landing robots on Mars. So that's going to make that part of the work easy, especially for an audience here that is used to thinking about the constraints on landing a robot on Mars. The concerns for the humans are going to be almost identical. So there's the summary of considerations that I mentioned, but for operability, we have one more to think about. Cooties, by which I mean planetary protection. Okay. This was mentioned before, and I understand this revelation was actually sort of recent for our planetary protection community. Suits leak. What? Yes, spacesuits all leak. Every seal ever engineered by a human being leaks. Suits have lots of seals, all those rotating joints, the gloves, the helmet, the waist seal, all that leaks. It has a spec leak rate. And they're like, what? No, suits are sealed, right? Sort of. They have a spec leak rate. And even in places where they work with, Ebola viruses and stuff like that, the people work in suits that are kept at a positive inside pressure, so they leak only outward, and that's a good thing. But the spacesuits are exactly the same thing. You mean the suits leak? Oh yeah, all over the place. And so do the habitats. They leak all over. So we're going to be venting bacteria and viruses all the time while we're on Mars. Sad fact. If we can't deal with it, we shouldn't go. There is no way to guarantee that a suit that's been outside and in contact with Martian materials is 100% free from any kind of biological, molecule or prion or virus or bacterium. You just can't do it. So you can't, not only can you not prevent the people from leaking out into Mars, you can't prevent Mars from coming back into the habitat with you. And you can come up with the most expensive equipment, the most time-consuming protocols that science can invent. You're not going to solve these problems, but you can very easily eat up all your budget and all your time on the surface trying to keep from contaminating the planet or keeping the planet from contaminating you. So we have a decision we have to make as a community. So we can go to Mars, go to a place that might be biologically interesting, and we can get a gold star for planetary protection by using all these protocols, and we get no work done whatsoever because we're so busy preventing contamination from one or the other. Or we can go to a biologically interesting site. We can just say, to heck with planetary protection. We're going to go around, we're going to collect our samples and stuff like that, and then risk doing something really bad, like badly contaminating Mars, badly contaminating our habitat with something that eats us or something. We don't want that either. Or go to a biologically boring site, and now it's going to insult all the geologists in the room, but that's the real reason we want to go to Mars, right? Is to see if there's anything living there or was in the past. That's what really makes most people excited. And remember, the taxpayers fund us, so we have to kind of work on what they think is interesting. But it makes the mission less interesting if we're going to a site that we know is biologically safe. So I would suggest that those are our options, and we do have a very, very tough choice we have to make. Yeah. Yeah, I guess we have the right people, don't we? So just like when they made Pluto not a planet anymore, the smaller the group you have, the easier it is to make a decision. All right. So then finally, just a reminder, we're used to sending robots to Mars. We've been doing that for a while. We're really good at it. When we're sending humans, there's some things we got to keep in mind. I like to say human spaceflight is interesting because it has humans in it. When we're in space, that includes the surface of Mars. Just keeping yourself alive takes a lot of time and effort. ANSMET veterans? Yeah. Okay. So we know this from the space station. We know this from working in Antarctica. Just staying alive takes up a lot of your work time. You have to get enough sleep. You have to feed yourself. You have to keep your body clean. If you're in a group, you have to spend some time coordinating what work you're doing. That takes time, especially if you're having to work with a distant mission control. They're going to send you a big pile of mail every morning. You know, the radio's not going to work too well because of the time delay, but they're still going to send you a big pile of stuff to read every morning, and then you got to send reports back. Exercise is still a question mark, not a problem in ANSMET. You get plenty of exercise, just getting your drinking water by pounding the ice, for instance. On space station, folks are exercising 2.5 hours every single day, and even that is not completely removing the muscle and bone loss that long-duration astronauts experience. We don't know whether the 3/8 G you have on Mars is going to be just fine and you don't need to worry about muscle and bone loss, or we don't know whether it's going to be as bad as 0G. So we have loads of data at 1G, we've got a little bit at 0G, and we got nothing in between. So we may have to schedule exercise. And you have to give people a little bit of off-duty time, or as happened on one of the Skylab missions, they shut off the radio and refuse to talk to the ground anymore. We try not to let that happen anymore. But when you add up all that, you're looking at sort of 17 hours a day that's sort of spoken for, and you can't work in that. Now you get 7 hours left of work, and part of that is spent just operating the systems that are keeping the habitat going. And there's very hard to reduce that. On shuttle, it was more because shuttle was all switches. Station, the crew doesn't have to do much of that because the ground is doing it all the time. They send 300,000 commands a year to the space station to operate it from the ground. We can't do that on Mars because it's too far away. We don't have the continuous comm coverage. We don't have the immediate feedback that your command got on board. It's just not going to work. So we think you may have to automate a whole bunch of stuff, and you may get about 2 hours out of the crew, each crew member, which leaves a big 5 hours a day to do the work that we were sent there to do, which is unfortunate, but it's going to be hard to make a meaningful improvement in that, in my opinion. So, summary and conclusions. The crew's stake in the landing site, all we care about is safety and operability. The identity of the site is not important. Low to moderate latitudes, free from dust, free from boulders, free from steep slopes is good, and the jury's still out on altitude. We have a tough decision to make on biologically interesting sites because planetary protection is going to conflict with doing the work that we're on the planet to do. and you're probably going to get about 5 hours a day of real work out of everybody. And that's all I got. Thank you. Sorry? Oh, yes, I'll take questions. Yes.
So given what you just said about planetary protection, wouldn't it be smart to have some better data than we do have on whether or not there is life on Mars before we send human crews?
It would be marvelous to have that data. It would also be marvelous to know under what circumstances Earth life really can survive. You know, there's a lot of ultraviolet light. It's very cold. It's really a pretty good sterilizing environment, but we still don't know. We don't know what possible configurations Martian life could have and how durable it would be. Yes, the more information we get on this, the easier it is going to be to make our decisions.
Joe Levy, University of Texas. From a crew point of view, do you think moderating your behavior on the ground to respond to seasonal conditions is something that's going to drive people nuts, or is it a good thing? So there's been some language that's creeped into our preliminary documents pointing out that maybe northern hemisphere is better than southern hemisphere because it's more clement, or low latitude is better than high latitude because it doesn't get dark and glary. But you know, in Antarctica, no science happens in the winter outside. So do you think astronauts on a hab on Mars would mind having a winter season for analysis and a summer season for being out on the ground, or would that drive people batty?
I do not know the answer. I mean, people do manage in Antarctica when you can't go outside very much. If it was me, so answering just for Stan, I like to go outside. So I would rather, even in the winter, if it was really cold and nasty out, I wouldn't mind, you know, suiting up, just go outside, get a little change of scene, you know, move my muscles a little bit. But that's going to be individual, and I don't know if there's a objective answer to your question. Yes.
Hi, my name is Nikki. I'm from the University of Hawaii at Hilo.
Good for you.
So about your statements on astronauts potentially being contaminated or something like that, don't you think that most astronauts would think it was worth it to find life somewhere and risk that? Is that even a question for us as humanity? Like,
so if you ask the crew members, sure, I'm game, I'll go, right? If you ask them to sign up their buddy, they're maybe but even we don't get to make that decision. So Space and Life Sciences Department sort of helps us out because we tend to take more risks as astronauts than we really should. So what they're thinking about is, fine, so you know, one astronaut comes back with purple spots all over him, but can we really let them come back to Earth now? So that's another deal, right? We got to think about not just the astronauts, but we do intend to bring them back. Thank you, we like that. But so we can't just be thinking of the individual crew member taking that risk. I mean, in my opinion, I don't think there is much risk. Mars rocks rain down on us all the time. Okay, but we are taking on that risk on behalf of the entire human race, which means that we have to be a little bit more risk averse than we would be just making the decision for ourselves. Does that make sense? Thank you.
This is Paul from Michigan Tech. Quick question. If I were there, I would like to go to the vertical cliffs and things like that, because I think that's where the most important geology and other things happen. What do you think about astronauts actually doing that work?
Like that painting of the guys rappelling? I think that's insane. Seriously. Suit weighs 350 pounds. That sounds very, very dangerous, and you'd have to convince me why the result would be worth it. And I rappel on Earth, okay? I did some rock climbing when I was younger. We still okay for time?
Hey, Stan,
Hey,
it's Jake from Goddard. Will the crew want to have some input into how much time is spent during stays in the rovers versus stays back at the centralized habitat? Because that's something that factors pretty heavily into how much we can explore this large exploration zone.
You know, I don't really think so. The habitat is probably going to have more habitable volume per person. So a background, Jake and I lived together in one of those rovers for a week. So we got to know each other pretty well, and we still like each other, so that's a good thing. So in the rover, you're going to be more, you know, packed in there with your crewmate, but you get to see new territory all the time because you're traveling. In the habitat, you have a little more space inside, but the view out the window is boring. So I don't think there's going to be a strong preference for staying at home versus going on the road, and I wouldn't expect that to be a driver of your mission design.
Kind of piggybacking on that with the rovers, not just time, but how far would the crew be comfortable getting away from their base habitat and the ascent vehicle in a pressurized rover in the event that the rover has a mechanical failure and they can't drive the rover back to the MAV or the HAB?
Okay, that's a super good question. That drove all of our excursions on Apollo because they couldn't get further in the rover than they could walk back with the consumables they had in their suit. And we'll have to decide how reliable we think the rovers are, and we'll probably have 2 rovers. And if you only had 1 rover, that decision is probably going to keep you very close to home, because you would want that second rover in the case the first one broke down, that you could drive out and do a rescue flight. But that's a really good thought, and that will definitely be driving our mission design. Right? Thank you all.
Okay, so planetary protection, perhaps a little bit more formally then. So John Rummel, former NASA Planetary Protection Officer, Cassie Connolly, present Planetary Protection Officer, Gerald Kimenek, the ESA Planetary Protection Officer. They're all in Spain talking about icy moons. So I'm here. I think I'd trade the venue, but not the company. So I'm going to give you a planetary protection overview, look at some of the issues associated with a human exploration planetary protection paradigm, acknowledging that it's all human exploration, but actually when we're actually sending humans to the destination. Some of the knowledge gaps, which are without, some of them have been highlighted in some of the questions as you're going around the room. Look at some potential paths forward and a summary. So here's the short version of the official documentation on planetary protection. The keywords are in red. We want to avoid forward contamination so that we don't discover life that we brought with us. We want to avoid backward contamination so that we don't release Mars material in an uncontrolled fashion to the Earth. And then we tailor the requirements according to the target location and the mission type so that we don't actually spend any more money, time, resource than we actually need to do to achieve the goal. So I thought I'd do a reverse planetary protection. It seems that with The Martian that science fiction is okay. I'm going back a ways to H.G. Wells and War of the Worlds. And I just want to point out that the Martian PP guys did a really poor job. I mean, the red weed contaminated everywhere, and the astronauts did not come back alive. The one good thing is they didn't actually get to take any astronauts back to Mars. So with that thought in mind, just flip the analogy back to us going there. The rules say that we need to avoid the harmful contamination of our target body and also adverse changes to the environment of the Earth resulting from the introduction of extraterrestrial matter. That's the international agreement that we, the US, have signed up to, and that, in fact, all spacefaring nations are signed up to. One of the things about planetary protection is, as we dig deeper into what the Earth is like from a biological perspective, we find all kinds of wacky organisms. In the time of the Viking landers, they didn't understand about tube worms that were 6 foot tall on the bottom of the ocean because the bottoms of the ocean were sterile, right? Effectively, if we're missing something that's that big, a whole ecosystem, well, we kind of need to be a little bit modest about how we regard the contamination of Mars by our activities there. So we have this knowledge dilemma. So we have, extremes of radiation tolerance, extremes of depth, extremes of age. We really don't know the answers for here on Earth, so we didn't ought to presume too much about what life is like on Mars. So we then have these two questions. How do we compensate for what we don't know about life? How do we compensate for what Mars is telling us with the recent discoveries and so on? And the short answer is the unpopular one. We should be conservative about that. And so for the astronauts to take risks is fine, but it didn't ought to be on risks on the rest of us. And that's kind of the position that the international community has had for a long time. So how do we do this for robotic missions? What's the sort of paradigm that we're working under? For Mars, we've broken the robotic exploration down into 3 categories. Lander systems which are going to places that not carrying life detection systems and are not going to places where we think Mars life might be. That's category 4A. Lander systems that are deliberately going to search for life, and they have a more stringent planetary protection regime. And then lander systems which are intended to enter what are called special regions, which are areas of Mars or areas or zones of Mars which have water activity above a certain level and a temperature above a certain level. If we're going to those places and RSLs are a potential special region, then we need to reduce the bioburden, the number of spores present on the spacecraft, by 4 orders of magnitude relative to the 4A categorization. So what does that look like in terms of an implementation? This is MSL, which had a total spacecraft budget of 500,000 spores, 300,000 for the landed hardware. And the impacting hardware was one minus the other. And it's not just the total amount, but also the density. So there's a requirement for the spore density on the surfaces of the spacecraft of 300 spores per square meter. So just to put some perspective on that, a single colony in a petri dish of a growing actively growing organism will have more than 500,000 organisms in it. So you can see from that the requirement is quite stringent for how clean we need to make our spacecraft, but we have a methodology for doing it, and we've done it repeatedly. The MSL actuals are there, and if you compare that with what was done for the last time we looked at the bioburden associated with a human spacecraft, that was there were some tests done on the Apollo 9 lunar modular ascent stage, and if you take the spore density they found, the range, and you take the mass they found, and do some arithmetic. I'm a biologist, so I do arithmetic, not math. And you come up with a number which is somewhere around 23 million versus a robotic requirement of 500,000. So you can see we're way out of bed if you're going to send a human system. That's not counting the 10 to the 14 organisms which are present in each astronaut as their gut flora, their skin flora, and so on and so forth. So we have this issue of sending a bioreactor and their hardware. That breaks the robotic planetary protection paradigm. And so what do we do then? So NASA has sought advice on this over time. The last time this was considered in depth was in 2005, where this group, the NASA Life Support and Habitation Planetary Protection Workshop findings were published under Hogan. These are their kind of 7 top bullets. The one I'll draw your attention to is number 5. Currently, it is not possible to provide quantitative planetary protection guidelines. So right now, well, going back to 2005, but the situation hasn't changed a lot. Right now, we don't know exactly what it is we should be telling by way of numbers for planetary protection requirements, because we don't have the information about Mars. Our knowledge about life on Earth is incomplete. But they did come up with this concept, which is kind of a miniaturized version of the exploration zone, where you would have areas of the surface which are permissible for access by humans, and areas which are restricted to robotic exploration, where you would have only clean robots going and doing the testing work. And you would obviously look to expand that according to your study. And this is kind of superimposed on a Mars surface picture, but there are no dimensions here, because we still don't have good enough data to be able to say what those dimensions should be in terms of relative distances from of a lab or a HAB from a clean rover site from a hypothetical special region of interest. We do have a set of exploration principles which came out of these discussions in the 2005 era, basically as a set of guidelines for folk who are looking at potentially doing human exploration of Mars. Looking at, first of all, the highest planetary protection priority is safeguarding the Earth from back contamination. The greater capability of the human explorers is only relevant if you can manage the contamination associated with whatever activity you're doing. And it is accepted that with present day technologies we cannot do this in a sealed environment. It's Stan highlighted that there will be dust associated with joints and moving parts and so on, which was part of the degradation of the performance of the Apollo suits was the lunar dust, and we can expect a similar thing to occur with Martian exploration over time. So in terms of specific guidelines, there's a recognition that human missions will carry microbial populations. We don't know how to sterilize humans. A quarantine capability is part of the guideline. The ability to segregate an infected astronaut from an uninfected astronaut or uninfected crew. And an onboard crew member should be given responsibility for implementing the provisions overall. There's an expectation that, or a guideline that the human missions would be developed encompassing both forward and backward contamination concerns, and combining the robotic and human aspects of the mission so that you can actually get pristine samples back to Earth and the crew back to Earth. And the requirement is that the special regions should remain pristine, so that any sampling of special regions would not be done by crew directly by crew, unless they can demonstrate that that activity can be done in an aseptic fashion. And then any uncharacterized Martian site should be evaluated before the crew access. It's going back to my comments about the landing zone there. So the expectation is that pristine samples from anywhere which might look like a special region should be handled as if it is a contaminated item. So think Ebola. So you're potentially looking at enclosing the samples to bring back to Earth, to manage it in an environment where you have the resources to study those things. The initial human missions should be based on a conservative approach. So I'm looking at the comments about, which is for the first mission versus a second, third, fifth, and looking at what you would be planning for that activity. Maybe the plant growth experiments come at the end when you understand what the human is doing, rather than actually mixing those two things together. And that, importantly, the planetary protection requirements for later missions should not be relaxed without the scientific consensus. The path forward from these set of guidelines, which don't really help mission designers design hardware, is to put together try and get from a concept to something which is numeric. In the same way as we have the 500,000 spores, which is clean enough for robotic missions, we need something similar for the human side. So there is now an NPI NASA program instruction for planetary protection for human missions, that we should be facilitating the development of the monitoring of microbial communities associated with human systems, that we should be mitigating and minimizing contamination release, and that we should be understanding the environmental processes on Mars, which are our friend in terms of implementing planetary protection from the point of view of the very cold environment, the UV environment, so on and so forth. And this was the starting point for a workshop which happened at the beginning of this year, looking at planetary protection knowledge gaps for human extraterrestrial missions, and is then a feed forward to an NPR, which will be the numeric requirements that NASA will follow going forward. So that's that. It was about 80 or so interdisciplinary systems engineers, program people, planetary protection people, microbial ecology specialists, and so on and so forth. And there is a report pending for that. But this is the kind of the eye chart for what came out of the meeting. The study areas, the gaps in microbial and human health monitoring. There's 3 colors there in green, and the study areas broke down into 3 teams and looked at different aspects of work to going forward before we can actually get to those numeric requirements. You can see a lot of them are in this survey and monitoring, which to a large extent can be done by work on Earth. A lot of the mission technology and operations, yes, we know spacesuits are leaky, but how leaky? What is the number? What is the number that you're going to expel when you have a new suit, an aged suit, and how will Mars cope with that, which is the 3rd section there. The nature of transport and contamination on Mars, how much can Mars take of human detritus, if you like, before it becomes a problem to us getting the science data that we want. Thanks. So the path forward, if you like, looking at our path forward to the exploration of Mars, part of that is to understand the performance of the hardware, the characteristics of microbiology on Earth, and what Mars does to that microbiology, in order that we can come to a picture of, how far down the road do we go from Stan's point of view to cutting corners on planetary protection. I don't think that's going to happen, but planetary protection may be revised in order to manage risk for us to do the exploration work that we want. The knowledge gaps that we address will, the more information we have from precursor missions, the easier it is to back off on some of those more stringent requirements to get to a point where operation becomes practical. So, key message, if we're ever going to answer those fundamental questions in a credible way, was Mars home to microbial life, and is it today? Could it be a safe home for humans one day? What can it teach us about life elsewhere in the cosmos, or how life began on Earth? What can it teach us about Earth's past, present, and future? Then we have to protect our ability to answer those questions without having previously contaminated or, essentially rewritten the answers, overwritten the memory on their file. So then planetary protection is a required part of the journey. So this is what I've covered. We need to resolve the missions, the issues for human exploration missions to Mars. There are guidelines in place, but there needs to be numerics to those in order that they can be implemented. The NPI is a guide for NASA's planning going forward, and look out for the workshop report, which is probably within the next month or so. And an early integration of planetary protection considerations is essential for the crew safety and mission success. And I'll be happy to take questions.
Sorry, Jim Head, Brown University. So I was just thinking about your, what Stan was talking about with the, contamination from the suits and habitats, et cetera. And you were saying that basically the question is how much can Mars handle, okay?
Yeah.
So I was wondering, kind of hard to get a sample of kind of figuring that out, but at the same time in Antarctica, when we go in the field in the dry valleys, obviously we're contaminating, but we're doing everything we can not to at certain levels. So has anybody looked at what a signature of human contamination in Antarctica that might give us some data on that? Do you follow me on that?
Yeah, so there is actually a recent work, and it's kind of a quick look-see published, not out of Antarctica, but out of a transit to the Arctic, to Devon Island. And Andy Sugar and Pascal Lee published some work where they'd taken a Humvee and they'd basically done a traverse, 600 kilometer traverse or something like that. And they looked at, what's life like in the Humvee from a microbiological perspective? What's life like 100 kilometers out, 100 meters out? I don't remember the exact dimension, but some distance away from the vehicle. And the issue there is they had very limited sampling opportunities, so they got effectively 0 results. But
which is good news, right?
Well, yeah, it's good news, it's great news, but it's not a comprehensive answer. Another aspect to this is what they did find is when they had these dishes out in these remote locations, or the samples taken from the remote locations, is that the very low abundance of material they found, biological material they found, had a strong bearing or a strong affinity with environments associated with the Far East, China, Japan, and so on. If you look at the prevailing winds, so you kind of suspect that maybe what they're finding there may have blown in. And so you have a sort of duration or a robustness of life on Earth issue to consider. Then how does that transfer to Mars?
Do you really think, I mean, what do you see as a path forward to actually getting the data about whether the contamination from humans will actually alter the Mars biosphere or whatever it is? I mean, I just see that as really hard to do, and I worry that we're in stasis for 30 years, you know what I mean?
Well, we can't be in stasis for 30 years if we're going to have an answer in time to do the engineering for
look at the other way. We're not going anywhere until we get the answer, and I don't see us getting the answer. That's my...
Well, there are experiments you could do to look at damage to biologic material on Mars, at Mars, but you would actually have to fly the experiment.
There's a partial... I'm sorry, there's a partial answer.
Excuse me, sorry, I had like a question first. Is that okay?
Can I answer
this
question first?
Yeah.
Thank you. There is some work underway, or there's just getting started now to get part of the answer to that, which is how much does a spacesuit leak, how much does a habitat surrogate leak, and it's being done on space station, and there are samples being gathered on, or will be gathered, from EVA suits while they're out in the hard vacuum, and from around some vents out of the habitat itself to try and quantify how much stuff is leaking now with current designs. That gives us a starting point to understand what kind of stuff and how much of the stuff is getting out of these current design systems. We can then look at, can we make them better? Can we make them better from a hardware point of view? And it also tells us what can we expect as a starting point for how much stuff are we going to actually release or could potentially release into the Martian environment.
We've got
Hi.
time for 2 more questions, and we have to break.
There's one up there.
Yeah, so I have a backwards contamination question. Part of the plan to go to Mars with ISRU is to find water ice and use that for drinking. We don't really have a way to say that any kind of decontamination process we have is actually going to decontaminate any water that we find on Mars. What is the planetary protection take on that?
Correct, and we haven't looked at it in that much detail. I mean, the engineering capabilities are there for, we know how to do it on Earth. We only expect that Martian organisms will be sufficiently similar to the terrestrial biology that we would be able to perform those same processes. That's my opinion, rather than an official opinion or a NASA position. But anything which is not carbon-based life, we wouldn't even know what and how to look. So we wouldn't even know that we had a problem. Dave? Oh, well, sorry.
Yeah. So this is kind of getting at what Steve was saying and what Jim was poking at. So Steve's saying that we're looking at ways to kind of establish the baseline for what the suits or what humans are producing right now as far as forward contamination into an environment. But how do you come up with that number of here's the target to reach? So like how was that established for the robotic spacecraft of the 500,000 total spores or 300 per square meter or whatever the number was? I mean, where did that come from? Was that just kind of a wag that people were like, yeah, 500,000?
So that's extensively based on what was achieved for Viking. So
right, but we didn't know.
Viking, the Viking approach was let's make this spacecraft as clean as we can, and not pay too much attention to how much it costs to do that.
Right.
Part of the reason for that was because Viking had a life detection experiment, and they didn't know very well how that was going to play on Mars, and they didn't know very much about the Martian environment either. Now that Viking provided that data, Mars is a cold, dry desert, then it was felt acceptable for the sort of general regions of Mars where that was true, a cold, dry desert, that the pre-sterilization cleanliness levels for Viking, which is the 500,000, the 300,000 number of spores, was going to be clean enough so that any one single landing event wouldn't contaminate Mars at a probability level of 1 times 10 to the minus 4th. So that was an assessment made at the time.
Okay.
And we've kind of carried that forward. Those changes were made in the 1980s to put those numbers in. And they've stayed with us with the addition of, what happens if there's a life detection experiment? Oh, what happens if there's a special region? Those two are kind of, add-ons based on new understanding as we've gone forward. So the policies as written are very much evolved, and we're looking at the next evolution associated with this activity.
Thanks.
We need to. We're going to take a break here for 10 minutes. We were trying to do it for 15, but we have a next session we got to get done before we have problems with the buses. So we will start 20 minutes after. We will start sharp at 20 minutes after. So we'll come rounding you up too. So thank you.